Hello everyone, I'm Luca Ferranti indeed, and today I will talk about the JuliaCon proceedings. But first I would like to clarify that despite I am the one person talking, this is not a solo project, it's not me alone. For example, with Ludovic Ras, other editor, we worked on this presentation. We have a whole editorial team, so I'm just like the messenger. But you can shoot me, don't shoot the others, because the mess up will be my own. So, first of all, what is JuliaCon Proceedings? Well, as the name says, it's the peer-reviewed journal of the JuliaCon conference. And in this talk, I will explain about why we have that, what was the motivation, how it works, and how people can get involved. So this is the website that you can see here. So we have this very flashy website, which was not working a few minutes ago, but now it's up again. And yeah. So why do we have JuliaCon Proceedings? Well, first of all, JuliaCon was inspired by the Journal of Open Source Software, JOSS. And if you go to the JOSS website, I think they have a very cool quote where they say, in an ideal world, we wouldn't exist, JOSS says. Because without taking a stand, or good or bad, in academia, you need papers often. So, and without papers, you can struggle proceedings in your career. However, often people who work on research software, develop research software which is used by other researchers, they don't get that much recognition for it. They don't get a paper to be cited. So JOSS, the Journal of Open Source Software, was invented to cure this symptom, this issue of people working on research software used by many, but not getting recognition in academia. So this was the motivation for JOSS. And JuliaCon Proceedings has a very similar philosophy. However, I would say in an ideal world, we would still exist simply because people enjoy coming to JuliaCon and writing papers. So we have a lot of people coming from academia doing research software, and we wanted to give them an opportunity, a mean to get more recognition in academia and to give them opportunity that presenting at JuliaCon can help them advance in their career, like collect citation metrics and so on and so on. So our proceedings journal is official, so to speak, in the sense we have official code, we are peer-reviewed, and when people publish in the JuliaCon Proceedings journal, it's indexed by Google Scholar so that it can bump your H-index if you're interested in that. It gets found, you get a DOI, so it's official journal in all possible ways. Yeah. And as I was mentioning, I'm not alone doing that. We have an editorial team of 5 people, and I'm Luca Ferranti, the second one. Then we have Mathieu from France, Dimitri, Nikos, and Ludovic. So we don't have that many submissions. We have 5 editors at the moment. It has been enough. And then some statistics. We have around 86 papers published and 18 papers under review at the moment. So we are much, much smaller than JOSS. And also our journal was started in 2019, so since 2019, these numbers. We have had almost around 200 reviewers. And maybe the metrics that everyone is asking, is interested about, how long does it take to get published in JuliaCon Proceedings? Well, let's just say that our review process.gl sometimes can have some pre-compilation time, because we are all volunteers-based, so sometimes things happen in life and things get delayed, but we strive to get a publication within 2 months, similar to JOSS. We have this 8 weeks round the period, which we strive for, but sometimes things get a bit slower, unfortunately. Yeah, and in terms of more technical details, how our proceedings work, so everything is automated. And we want to make the review process as easy and enjoyable for people, so a bit less bureaucracy, less overhead than traditional journals. So everything happens on GitHub. Similar to JOSS, everything is fully open, so the review process is open. Everyone can see who was the reviewer, what the reviewer said, how the author replied. So fully open, fully transparent, and yeah, on GitHub. Then we actually use the same code of JOSS, so the same infrastructure of JOSS. We have a very strict collaboration with them. They helped us set up everything a lot. And we had a technical revamp in late 2023. So before we were using this old Widom bot, which was JOSS' previous bot, and then we had this technical revamp to use the new editorial bot, which is allegedly better. And so we revamped the website, revamped the app, fixed a bunch of bugs, and so on and so on. Then, to give more in details, then this is my last theoretical slide, so to speak. Then we will go around and have a more hands-on tour of what we have and what one needs to do a submission in JuliaCon. So here I highlighted the most important repositories of our infrastructure. So the first one is this JuliaCon submission.gl, this template which lives in the JuliaCon organization on GitHub. And this is the LaTeX template for the submission. So different from JOS, we don't use Markdown, we use LaTeX because a lot of people at JuliaCon are pretty like, math heavy, math hungry in their papers. So we need a bit better support. So we use the LaTeX template. There was a talk last year from Patrick Altmaier about making a copy of this template in Quarto. So it's a bit work in progress, but ideally soon we will have also the opportunity to publish in Quarto if you don't want to use LaTeX or support simple Markdown. And if someone is interested in Tipst, wants to support Tipst, ping me and we can arrange that. Then we have this proceedings reviews repository where, as the name suggests, all the reviews happen. So all the reviews are as an issue in this repository. And the papers repository, oops, here should be a dash, where we have the PDFs of the paper and the metadata as XML, which is used to load the data in the website. And finally, our website itself, the web app, actually lives under JOS, the JOS repository. So in the Open Journals organization JOS repository, we have this JuliaCon branch where all our gigantic Ruby code for the whole app lives. So yeah, now we can have a short tour a bit. So as I was saying, this is the template for the paper. So the first thing, if you want to write a paper, would be to use this template, fork the repository and start writing. At the moment, we only have LaTeX. Yeah, we currently use LaTeX Make for compiling. Before the revamp, we were using some old version which apparently disappeared from the internet. It's actually the only thing I never managed to find in the internet. Now with the revamp, we have a bit more stable like Docker image, so you can also check like if you want to get the exact same compilation environment, you can run in a Docker image. So this would be the first step if you want to publish to the paper, to go to this repository, take the template, write the paper. And also, importantly, the paper, in general, if you're presenting a package, the paper should live in the same repository of the package, which is the same rule of JOS, basically, because JOS publishes only software, so the paper is a subset in the paper. Then you can choose. Some people don't want to have in the main branch so that it doesn't get downloaded every time they install the package, so you can have in a separate branch if you want. Then in JuliaCon, since we also have a more like traditional academic audience, often we also have traditional research paper in the more traditional sense. For this, in JuliaCon, opposed to JOS, we also allow like separate repositories. Like if you're not proposing a new software, but just like doing, but doing some experiments on that. So yeah, that's maybe a difference. Then after that, you would go to the JuliaCon website, which is this proceedings.juliacon.org, and you need to log in using the ORCID, so you need the ORCID identifier. Once you log in with it, you can make a submission. And what happens once you make a submission is that it will appear to us as editor in this dashboard, which I'm not now showing because we have some unpublished stuff still. So it will appear to us, and then we will start the review process. And when we start the review process, we would go to this proceedings review repository. And here, this repository basically has only issues, and all the issues here are reviews or pre-reviews. So the first step would be a pre-review, and during the pre-review, the editor will look for reviewers. And once the reviewers are found, we will start the review. And then in the review, if I take maybe a concluded one. In the review process, the reviewers will discuss with the author, give feedback, and so on and so on. So it's a very constructive, iterative process, a back and forth. We, in a way, funnily, we don't reject that much because our scope of the journal is not to give an assessment, good, bad, but to help people improve the world so that in the end, everything becomes good. So it's a bit paradoxical that we don't have rejection rate. But yeah. So here we have this editorial bot which does some automatic checks. So for example, checks that all the references have a good DOI and so on. And then reviewers and author can discuss. And the bot will generate a review checklist for each reviewer. And then the reviewer will check the software, check the paper, give a feedback, and so on and so on. And once the process has converged to the good and the review is completed, the editor will pull the trigger. And when that happens, we have this other repository, these proceedings papers, where all the papers are stored. So each folder is a submission, a paper, and this will contain the PDF of the final paper and an XML file, which is used for rendering the information on the website. So if we check the website, here we have a list of papers, and all these info, all this metadata here is rendered from that XML file. And a thing to notice is that I said our process is fully transparent, all the reviews are open, so you can also see like the reviewers in the final paper. So in a way also reviewers get credit for having reviewed. That could be a way of seeing it. Yeah. Yeah, and in terms of next timeline, we generally start the review after the JuliaCon. So if you present at JuliaCon 2025, after the conference, we will make an announcement, hey, if you present at JuliaCon, you can submit a paper. The timeline is still a bit work in progress, but around like late fall 2025, we will open the submission, then everyone can submit, and later 2025, early 2026, we will start the review process for the 2025 batch. And if you want to help, we need a lot of volunteers because yeah, we get some papers and everyone has limited time, so we need help. So if you want, please make sure to submit as a reviewer, volunteer as reviewer. So we have this gigantic button, volunteer as review. It's a short form asking you for some keywords of what you're confident reviewing about, and then you are a reviewer. And then we will ask you to help. So yeah, that's it. Hopefully you hopefully if you didn't know about the journal, now you know, and hopefully a lot of people will submit and we can grow the journal. And if you have any questions, please ask.
Yeah, I think this is very important, and this is great to see that, and yeah, really important. And I'm wondering, like, I mean, this is completely free, which is great, but then what happens if there are some, like, does it just depend on one person? Like, I don't know, like the head of the project, if he leaves, then what happens?
Yeah,
I'm
so
just wondering that.
yeah, so excellent question. So we don't have a bus factor of 1, likely. So as I showed, at the moment we have 5 editors, and also in JOS, because JOS is much bigger, they have like a more stratified hierarchy of like editor-in-chief, editor, and so on. Here we only have 5 editors, and we all have admin rights. So if any of us gets hit by bus, the other 4 are able to keep pushing, and yeah. And also like for the more like technical deployment part, we get a lot of help from the YOS people themselves, like deploying the app, maintaining the app, the database. So they also have access to it and they can help us if needed. So yeah, we don't have a bus factor of 1, but bus factor of 5 at the moment, which is acceptable.
So my question is regarding so you open up the submissions after the conference ends, and obviously it'll be very important to the journal and the conference that many people who present submit. I'm just wondering, based on previous conferences, do you know like what the yield rate is for people submitting journals based on who gave presentations? Yeah, so we are still a bit like in transient phase because we had like this technical revamp that we needed to do, and that of course like affected the number because the app wasn't working, so people weren't submitting, and then 1 year later they didn't care about submitting again. But I think we get a few like tens of submission from the main JuliaCon, a couple of tens. So great. Yeah. Thank you.
Yeah.
Is there anything else? Okay, let's give our speaker one more round of applause. All right, the next speaker can get ready, and then when it hits 10:30, we will start. Yeah, there's a talk at 10:30. The speaker just must be coming from a different room.
How long are you using Julia?
I'm sorry.
What? How long you have been using Julia? I'm pretty new.
I'm pretty new too. I've only been involved for about 1 year, but very
Are you a
loosely.
student here?
I'm a student at Pitt, yeah.
What is your program?
Civil engineering. I don't use Julia myself. Hi, everyone. Thanks for coming. I just got word that our speaker will be a few minutes late, but not so long. So please hold tight, and we look forward to hearing him.
All right, awesome. Thank you.
So I'll be holding up the pieces of paper to let you know.
Okay. Cool. Thank you. You know what? It prompted me and then it disappeared, so maybe I'll try that again. Yeah.
So system preferences, maybe?
Yeah. See if it'll
Or
different.
sometimes the restab also helps it to work.
I think you need to go to the settings.
Okay.
Yeah, let's go to system.
I was having trouble finding it. Team display.
Yeah, display.
Is it advanced?
So you click ask click to share.
Errors are probably fine.
Maybe go up to the menu that it was asking you to. Up here.
Oh, there's a menu up here.
Hearing.
Yeah, Black Magic is over 0.2. So
Screen start.
there it is.
There we go.
Let me check and make sure we have it in there first.
All right. Okay. I'm Stefan Karpinski. I am the Chief Product Officer at JuliaHub. I'm probably the only Chief Product Officer that spends this much time thinking about floating point ranges. So this is what I'm going to talk about. Floating point ranges, why are they hard? Can we do better? So why are floating point ranges hard? Consider this innocuous looking range, 0.1 to 1.7 with a step of 0.2. Let's, try to generate the values naively, the most obvious thing you would possibly do. So, you put your start, 0.1, plus integer multiple of the step and, the correct length, which I just figured out by hand, and oh, oops, okay, we get very messy looking numbers. Those are not the values we actually wanted. All right, so why this is happening, this is actually the source of 99% of confusion about floating point, is that 0.1 actually means this kind of nasty number. It's, every floating point number is of the form integer times a positive or negative power of 2. So, every fraction you're approximating is you're finding something of that form that's as close to the actual value 1/10 as possible. In this case, 0.1 is slightly higher than the actual value 1/10. 0.2 is slightly higher also. 1.7 is slightly smaller. So obviously you can't take a thing that's bigger than the true value plus a thing that's bigger than the true value and get a thing that's smaller than the true value. It just doesn't work. If taken at face value, these values, they're just incoherent, right? Like we don't have a workable range if we take them literally. That's normally what we do with these things. Like if we evaluate sine of 0.1, we don't actually compute sine of 1/10. We're not guessing that the user actually meant 1/10. What we say is, okay, well, that float value, even though we write it as 0.1, actually means this. We're going to compute the sine of that and then round it back to float. That's what we do. That's normally what we do. It's a sane thing to do. But in this case, it's incoherent, so we can't do that. Okay. So sadly, we need to do some amount of guessing here. Each value that we're getting has a bit of wiggle room. Yes, it has a true value that we often use, but also there were a bunch of real numbers that would round to that number. So any of those would actually be a valid interpretation. And so the question is, can we pick real numbers for all three of these inputs that agree with each other and actually hit the endpoint, and which all round to the correct values? Here's another example just to show some more nastiness. So this is another case where the true values are off of what you expect them to be, and you see that this is partly to show that our current implementation is not perfect, right? We do get this earlier example correct these days, but we don't get this one right. We don't hit the endpoint correctly, and then the midpoint of this range should be 0. It is not 0. It is 4.3 times 10 to the 9th. That's a lot. That's very far from 0. That's not the same thing. Okay, and this is a similar thing where the true value of this floating point number is these nasty things, and then if we put the little bit of the wiggle room due to the epsilon of the float, that's how much wiggle room we have. So what we really want to do is say, are there some integers in these ranges that we could pick that would make this thing work? And obviously there is, because that's the thing you had in mind when you wrote the range. But the question is, how do we do it algorithmically? How do we actually figure that out? Here's what we do now. We guess what A colon S colon B means. We compute the length by doing a division and rounding. So if there's going to be a length, that's what we think the length will be. Then we try to rationalize A, try to rationalize B. So by rationalize, I mean consider the interval of numbers real numbers that round to that, or rational numbers that round to that, and pick the simplest one. And there's an algorithm for that. It's actually very cool, very clever, but you don't need to know about that. There is an algorithm. And then we compute given those rational endpoints, what would the exact step be? And then we see if that actually rounds to the step we were given. And if that checks out, then we've got a good interpretation and we can just go with it. If that doesn't work, then we have to fall back to the literal bad interpretation and we get these kinds of results. So it would be nice if we had something clever where this worked more of the time or worked all of the time. That would be amazing. One of the issues here is that when you rationalize A and B independently, you may not get an answer that actually, can be made to work. You might need to consider them together to get a correct answer that actually is workable. All right, so let's formalize things a little bit. We'll view float inputs as intervals because that's more convenient mathematically, and that's like the set of real numbers that they could have been. So I write, capital letters for the intervals, and I use minus and plus for the low and high ends. So a rational interpretation of a range is a triple of rational numbers that are in the appropriate intervals that you were given, and such that the start plus the length times the times the step is equal to the endpoint. So we actually hit the endpoint exactly for some n. We don't know n, we're not given n. I'll refer to n as the length here. It's not the length in the sense of it's the number of points you get, but it's the number of steps, and it's more convenient, and it's nicer usually. For example, in this one, the actual length as a collection of values is 2e6 plus 1. You're like, no, I want 2e6. That's the thing I'm interested in. The grid unit. So this is if you have a rational interpretation, you can take the GCD of those rationals. So it's the greatest common denominator, and the definition there is just that these ratios are integers. It's the biggest value such that those are still are integers. And then those grid ratios always have a GCD of 1. They're always coprime. Okay, so the question is, how do we pick from all of the infinite interpretations? If a range specification is feasible and not degenerate, like empty, 1-point intervals, then there's an infinite number of interpretations, and how do we pick a good one? This is the whole problem. And good one here means, it's weird, it's kind of definitional, like we get to define what it means to be a good one because nobody's giving us a definition, but we want it to match intuition. And we need it to be computable. So this is sort of the pull and push of this whole thing, is like we want something that agrees with what people intended, but also we can reasonably compute it. Okay. So one possibility that I was chasing for a while was the simplest grid unit that would make it work, and this is equivalent to computing some intervals for things, and then finding a denominator that simultaneously rationalizes them both, which turns out to be a very interesting but also very hard computational problem. And one thing I realized later after chasing that for a while was that tends to violate invariance that you actually really want to hold for this. And what I mean by invariance, I have to talk about transformations first. Here are some transformations you could do to an interval. You could scale it, so just multiply all of the things by some real constant. You could translate it, so that doesn't touch the step, but it does touch the start and the stop. I've changed the order that I'm writing A, B, and S here, sorry, but you'll follow. So that makes sense. If you translate it, certain things should be the same, like the length shouldn't change, the length shouldn't change for either of those. That's sort of like a hint of what I mean by invariance. And then there's this last one that it took me a while to sort of hit upon. It's this concept of refinement. If I cut the step in half, it shouldn't really change the endpoints, but it should just make the length twice as big. And for various reasons, we're only interested in binary refinement. If you allow arbitrary refinement by arbitrary integer constants, you end up forcing weird prime numbers into the length, and that's not what you want. But with 2, it's safe. It's actually quite good, and it's a nice property to have. So here are the invariants we end up wanting. So length should be scale and translation invariant. And I've written this in Julia syntax, but it's actually a little bit misleading because, of course, if you multiply the floats here, you're not going to get exact invariance because there's round off with the multiplication. But what we're actually talking about is translating the exact mathematical intervals. So if you scale the intervals and you have a reasonable algorithm, in the in math world, in exact arithmetic, then it should give you these same answers. In floating point arithmetic, this wouldn't give exact answers. But if you had, for example, if you scaled by something that had no error, which is only multiples of 2, powers of 2, but then it would actually work. So translation also. Now the ratios, what I mean by ratios is those grid ratios. So if you return the tuple of grid ratios of your interpretation of a range, the grid ratios shouldn't change when you scale or do binary refinement. And in particular, the grid ratios don't include the length. So when you do binary refinement, of course, it changes the length. And here's the relationship we want for the length, is that if you cut the step in half, it should double the length of the range. Okay, well, so with those invariants, I spend a bunch of time noodling and figuring things out, and let's look at these invariants versus the simplest rational approach. So the rationalized function, it does, it finds there's a unique simplest rational in any interval, which is actually a cool, deep mathematical fact based on something called the Stern-Brokat tree. And it's how our current range interpretation works and how the rationalized function works. But it's terrible it doesn't commute well at all with scaling and translation, even mathematically, right? Like it's not just a floating point issue. When you look for the simplest rational in an interval and then you scale that interval, you do not get the scaled version of the simplest rational. And same thing with translation; it totally messes with things. So this turns out to be this is bad. Using this if we use the simplest grid unit approach, we would like totally violate our invariance left and right, which is it's both like undesirable, but also the real reason it's important is that those invariants tend to be true of the interpretations that people intended, right? That's the real reason we care about them. It's not like, oh, these nice invariants hold and math is pretty. It's, okay, the thing the person had in their mind tends to respect those invariants too. So if we have an interpretation that respects those invariants, we're more likely to find the interpretation that the person actually wanted. So I developed an algorithm for this. It's extremely hard to compute efficiently, and like I said, it violates the invariance badly, so that was a dead end. But I learned some cool math. All right, so lo and behold, I'm just going to give you the algorithm, and I'm going to try to explain what each of these steps means. It has 13 steps. All right, so first of all, if 0 is in the range of steps, then the range is infeasible, because you can't have a 0 step and go anywhere. If this is just one of those things where like these types of computations don't work out if the sign is negative, so flip the sign, make sure S is positive. If n is now you compute the lower bound on n, lower and upper bounds on n. So this is like the feasible length of the range, because we don't even know the length of the range. Remember in the beginning we computed b minus a over s and then rounded it? Sometimes there's more than one integer that could be in that. So rounding isn't always the correct thing to do there, unfortunately. So what we have to do is compute this. I think one of these should be a ceiling and one of these should be a floor. I believe the one on the left should be a floor and the one on the right should be a ceiling. Yeah, so anyway, so you have the bounds on the possible integers. You compute this. If this range is empty, you have an infeasible problem. We actually do a thing for that. If it's infeasible, if you can't hit the endpoint, we just stop at the point before the endpoint that was given. So that's what you would do here. You would just be like, okay, well, I can't interpret this. I'll just take it literally and stop before the endpoint you gave me. So now in that interval n, you find the integer with the maximum number of trailing zeros as a binary integer. Now this is the first heuristic I came up with here. Because, one of the things you're looking at is you're like, you want a nice n, right? And what does it mean for it to be nice? And is there a version of nice that we can compute easily? So, you know, one of the things you have is like, well, yeah, it's like a small integer times the power of 10. That's often what you meant. Sometimes you also mean like a small integer times the power of 2. That's also another common thing. As it turns out, 10 is divisible by 2. Deep facts here. That's very convenient because what we can do is we can actually just look for the number with as many trailing zeros as we can, and we tend to get nice like multiples of powers of 10 and multiples of powers of 2 there. Just happens to be that these are the number systems we work with. If you're doing, you know, a small multiple of a power of 7, you're kind of shit out of luck here. Sorry, like it's just not going to work as well. But that's acceptable. I mean, this only kicks in the case where like the epsilons are really big. So a lot of the time there is only one integer in that you could possibly pick, and this kind of doesn't matter. Another nice fact about that is that there is a single unique integer in any interval that has the most trailing zeros. So that's nice. Binary, yeah. If we could do it in decimal, that might be nice too, but it's too inefficient. We want to do it in binary. And the good thing is that doing it in binary tends to get you the nice decimal ones anyway. Okay, so now we let p equal the number of trailing zeros of n. And then what we do is we take n and a and b, and we divide them by 2 to the p. So basically we lop off all the trailing zeros on all of those things. We shrink them down. And now we compute this q bar interval. And essentially what this is we're looking for the interval where our like a over b ratio could be, or sorry, a over s ratio could be. So we have those like grid ratios, and we're putting a bound on where the ratio a over s could be, the lowest and largest and smallest number that a over s could be. And then we're going to try to figure out what a over s is. But, and this is the thing, we've done it in this reduced space where we have divided by 2 to the p. And the reason you want to divide by 2 to the p is because of the refinement invariant. And this is a little hard to explain. I should have had a slide or something for this, but there were too many talks to prepare. So the finer your grid is, the more likely you are to sort of hallucinate the property you want of it, because it's just kind of like, oh, this thing happens to line up in a right place. So what you actually want to do, I put it as refinement because it's simpler to state the invariant that way. But what you actually want to do is you want to take your grid, and then essentially what you're doing when you're taking this dividing by 2 to the p is you have a grid, and it's got like a lot of steps, because now you know your ends, you know how many steps there are. And what you're saying is like, you know what, let's just make our steps bigger so that there's an odd number of them. It's the biggest we can make the steps without changing the properties of the range. And when you do that coarsening is a good way to sort of avoid hallucinating properties of the range. And it makes that invariant hold by basically saying, okay, whatever version of this I found, like let's suck out the powers of 2 to the p and then work in that, you know, maximally coarse version of the range, and then that's the properties we actually want. So there's 2 cases here. If that range contains integers, that's what this property says, is like, is there an integer in there? Then we just say that our grid ratio can be, you know, an integer over 1. So a over s can be an integer over 1. And that's what we do. We just say like, okay, we pick a to be the nicest integer in that interval, and we say s. And again, it's s, a bar, and s bar. We say that a bar and s bar, a is an integer and s bar is 1. Otherwise, we have, you know, this q minus and q plus. This q interval doesn't contain any integers. And we take the fractional part here. That f should have a bar, but it doesn't matter. and we find the simplest fraction in there. I actually think this is equivalent to finding the simplest fraction in the Q interval, but it's just easier. The numbers are smaller, so that's what we do. And then, you know, whichever way we did this, we can get B. And so now what we have is we have our grid ratios, actually. So what we have is that we've essentially got our interpretation. We've got N, and we've got the math letters A, B, and S. And what we have is our interpretation is now alpha is A over S, beta is B over S, and N is N. And so we've almost got our range interpreted now. We know the ratios, but we don't know the actual grid unit. But we need to go back, we need to put those powers of 2 back in. This is just very mechanical. You just put the powers of 2 back in and keep it reduced. It's not a big deal. So now we actually have our fully re-expanded A, B, and S. We have our ratios. All right, so now we want to find the grid unit. And the way we do that is we take our intervals that we were given, and we divide by the integers. And now this is basically taking, we have this interval over here and this interval over here and this little step interval. And now we're projecting those all onto the grid, and they should all overlap. If they don't overlap, you've got trouble and the algorithm is broken. But they should all overlap and intersect, and the true grid unit is in that intersection. So now you just have one interval, you find the simplest fraction in that interval, that's your grid unit. Once you have your grid unit, all of the values in your, we have the grid unit as like a rational, right? And so then what we do is we take it from a rational and we compute in double precision. So we don't just do one float division, we do like the float division and then like the error of that. So now we have the grid unit at high precision as a float. And we can do a fused multiply add to get any value in the grid, and it works. Like this actually gives you correct answers. All right, so let me do a very quick demo. Okay, okay. All right, so I have this function called lift range. Okay, so we have our range, and you know this is the example that works horribly before in current Julia. All right, so you know, can we lift it with the new lift range algorithm? Da 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 da. Moment of truth. Yes, it works. And if we collect the values, they are exactly the values you want. All right. Another fun thing we can do is we can, you know, this is a subroutine. We can just ask what the range ratios were. And so what this tells us is that the length of this thing was 7, okay? And that that you know the A integer is -3 and the B integer is 4 and the S value is 1. So now you know like the ratios of everything as integers, but I return them as floats because they have better range. And we can see this is actually like a horrible hacky version of the code. I really need to do a better version, but I ran out of time. I think this is the file. Yeah. Okay, so I will. It works with yeah, it'll work with any step range, and it doesn't really care about the fact that lengths have to be integers. This is the actual code. I mean, I'm not going to go through it. It's just like I'm just showing you the horror show. So that's the lift range part, but then there's the range ratios part, which is all of this nonsense. It's crazy. I think it can be made simpler and faster. But anyway, I have like 1 minute for questions. Does anyone have a question? All right.
How fast is it?
Currently slow, but I think it can be made fast. I don't think there's anything in there that's like horribly slow. Basically, what you do is what you want to do is take the floats, convert them to integer ratios with a floating power of 2 in there, and then do everything in integer arithmetic, and then until at the end you produce 2 floating point numbers. One more question, maybe?
Not sure if you're familiar with like posits or other like floating point alternatives, but will this algorithm generalize to those? Have you looked into whether that's like a good general solution for any given arbitrary number type?
Yeah. I mean, there's nothing floating point specific. The inputs are intervals of real numbers. The output is a rational number. So all the internal stuff is actually like not floating point at all. It's all done you want to do it in exact integer arithmetic. Okay, thank you.
We have an adapter over here.
Okay.
Yes, that's the new MacBook. You should need the adapter. But we already have one for you. You don't have to sweat it.
Okay.
Just grab it so it doesn't.
Okay. Thanks.
Yep.
Okay.
All right, everyone. Thank you for attending the next talk here. We'll let our speaker introduce himself and the topic. Please give your attention.
Hi, I'm Cameron Begonik, and I'm here to talk about multiple interfaces today, which is a package I've worked on for a while now. So, multiple interfaces provides a way to work with and define interfaces in Julia. You can define an interface as a list of required methods. You can create new interfaces that extend one or more existing interfaces. You can also declare the interfaces that different types implement, and you can also use multiple dispatch on these interfaces and even interface intersections too, which is something that Kobe mentioned in his talk today. And you can do all that with no runtime cost. Okay, so let me talk a little bit about the motivation for this package, why I was motivated to build this package. Let's consider this example of writing a second function, which is to get the second element of a collection. You might want to define two different implementations for this function, one which dispatches on an iterator, and one which dispatches on a indexable object. But as you're probably well aware, that can't really be done right now because the iterator interface is informal and it does not have an abstract iterator type. And the same thing goes for indexability. So we could fix this if Julia had abstract multiple inheritance, which is the ability to inherit from more than one abstract type. So in this example here, you can see I have this hypothetical example where we have multiple inheritance. We could define the array type to inherit from both iterator and from abstract array. So now you could send an array type to the second function, and it would dispatch to the iterator abstract type, and then our problem is solved. Here's just kind of another motivational example, which is designing graph types. Designing graph interfaces is challenging because graphs can have a lot of different traits that you want to try to encode in your hierarchy, but that's hard to do with single inheritance. Here's an example where I start out with just a very basic graph type at the top, and inside the boxes there's a list of methods that are associated with each type, or interface if you want to look at it that way. So we've got two types that inherit from graph. We've got an undirected graph type and a directed graph type. they each have their own edges and neighbors methods that are different. But then you also want to be able to address mutability of graphs. So there's a mutable undirected graph type, which inherits from undirected graph. And there's a mutable directed graph type, which inherits from the directed graph type. But unfortunately, as you can see, they have exactly the same interface. They have the same the same list of 4 methods that are required for mutability. So why do we have to repeat that interface across 2 different abstract types? It's not exactly ideal. Okay, so let me go into a little bit about how multiple interfaces is actually used. So you can define an interface with the interface macro. We have an example here on the left where I'm defining 2 different interfaces actually. First, your functions that are in the interface have to actually be defined. Otherwise, you'll get an undefined variable error when you use the interface macro. So first I define the functions A1 and A2, and I define an interface A, which consists of the methods, or the functions A1 and A2. And similarly, I define an interface B, which consists just of the method of the function B. And then on the right, we see that you can actually extend existing interfaces, and you can extend more than one. So this is where the multiple inheritance comes into play. This interface C is extending both A and B, and it's adding this function C. The extension is to add the function C to the interface. So extending an interface means that you're basically adding on to existing interfaces. So this diagram on the left kind of diagrammatically shows this multiple inheritance that we've got here. So in order to implement the interface C, you have to also implement interface A and interface B. So I have some just utility functions here that allow you to query what are the required methods of an interface. So the required methods function, as you can see on the right, when you call it on interface C, it just tells you the functions that are declared to be part of the extension, which is interface C, the ones that are explicitly declared in the interface declaration for C. So that's just the function C. But of course, C extends A and B, so in order to actually implement C, you have to implement A1 and A2 and B also. So to get that full list of all the required functions that you need to implement, you can use the all required methods function on this interface C. So it returns the list A1, A2, and B and C. Okay, so now we need a way to declare which types implement which interfaces, and that's what the type macro does. So in this example, I've got 4 different types actually. Ant, bear, cat, and mouse. Ant implements A, bear implements B, cat implements C. And we see here that mouse implements both A and B. So you can provide a list of interfaces that are implemented by this type. One thing to note though is that, so take this example, cat implements C. Remember that C extends A and B. So in order for cat to implement C, it must also implement A and B. So that means that these 2 declarations on the right are actually equivalent. So you can, if you want, you can just use the one on top, cat implements C, and that implies that it also implements A, B, and C. Or you can explicitly list them all out like this on the second example if you want to. They're both equivalent, so it's up to you which one you use. And it turns out to be very useful to define interface intersections. A lot of types implement more than one interface. And so the way that you represent that is with an interface intersection. And we can create interface intersections in this package by using the ampersand operator, the AND operator. And it has some nice properties. It'll automatically simplify the intersections. So like here, if you intersect an interface with itself, of course you just get the original interface. So A and A is just A. A and B can't be simplified. So it's A and B. These are the same interfaces that are defined here. But also the order that you intersect the interfaces doesn't actually matter. So A and B equals B and A, as you would expect. And here's another case that gets simplified. Because C extends A and B, the intersection of A and B and C is just equivalent to just C by itself. So this simplifies to C. And so does this longer version, A and B and C and B and A. That also simplifies to C. Okay, finally, we need to be able to dispatch on these interfaces, and that's what the iDispatch macro does. So you can create methods that dispatch on both types and interfaces. And I call these methods iMethods, which is short for interface dispatch methods. So here on the left, I have an example where I've defined 4 iMethods for the function foo. And you can see they dispatch on both types and interfaces. So you use this colon syntax in order to define a dispatch on an interface. And note in the third method, we've actually got the third argument is dispatching on an interface intersection. And so we've just got some examples on the right of the dispatch in action. You can see in the first 2 examples that the dispatch on types does work as expected in the first argument. And then you can see down here in this example, we use mouse for the third argument, which if you recall, that mouse implements both A and B, so it matches this method here. It's the same as in regular Julia. We pick the most specific matching method. So in this case, for this call here, the most specific matching method is this third method here. And note that in this last example, cat implements C, which is actually more specific than the intersection of A and B because it adds one additional method. You know, it extends in A and B by adding one additional method. So it's more specific than the intersection of A and B. So this last call dispatches to the last method. Okay, and you know, a lot of people are interested in performance in Julia, so it's important to know that the interface dispatch that this package provides compiles away. So here's just a simple example where we have a type crow that implements Q, and we have 2 iMethods, one that dispatches on P, one that dispatches on Q. On the right, we can see that all of the dispatch infrastructure in multiple interfaces basically just compiles away, and it just returns the integer 2, which is what we expect. I've also got a benchmark here that shows that, you know, it's really just returning the integer 2. There's no allocations. It's very fast when you call bar on a crow. Okay, so the reason I implemented this package is because multiple inheritance is a powerful way to express the relationship of various interfaces. It's influenced by other languages that actually have this, like Haskell has type classes, Rust has traits, Java has interfaces, and they all support some version of abstract multiple inheritance among those, among type classes, traits, and interfaces. And here on the right, you can actually see this diagram from Haskell of a very rich hierarchy of type classes in Haskell and what they call the prelude. So it's kind of like core or base Haskell. So in multiple interfaces, actually all the interfaces in the required methods list, they're all required. There are no optional interfaces. But because we have multiple inheritance, we can still express complex combinations of interfaces, complex combinations of, you know, selections of the interface methods that we care about by using the multiple inheritance. So we get the nice property that there's no optional methods, which can be kind of a pain in the butt to work or just to understand and work with. So we get the nice property that all the methods are required, but we also get flexibility with multiple inheritance. So there is kind of an open secret of this package. It's not really about interfaces. It's actually an alternative type system with abstract multiple inheritance. So this has a few consequences. It follows kind of the ethos of regular Julia, where the types, the abstract, in this case, abstract types are the interfaces, and multiple interfaces does not do any kind of enforcing or checking of the interfaces. So it kind of takes the traditional Julia approach of relying on doc strings and unit tests to basically define and test an interface. So I recommend, for interface authors to provide some kind of interface unit test suite, possibly with the help of a package like supposition.jl. I should note that there's some things, of course, that multiple interfaces does not support that are supported by the regular type system in Julia. Things like parametric types, there's no unions. Although personally, I think that parametric types shouldn't normally enter into an interface. That's more of an implementation detail. Okay, so I skipped over the section slide. There are probably some people with questions about ambiguities. So ambiguities can happen when you have multiple inheritance. Even when you're just dispatching on a single argument, you can still have an ambiguity. So here's an example of a dispatching on a single argument where we end up with an ambiguity due to multiple inheritance. So in this example here, we've got two interfaces, bar and quux, which each have one method. There's a type, cheetah, which implements both of those interfaces. And then we have two I methods for this function ASDF, one which dispatches on bar, one which dispatches on quux. So obviously, if you try to call ASDF on a cheetah, it doesn't really, the package doesn't really know which method to call because it could be either one. There's really no way of knowing. It's ambiguous. So it just throws a ambiguity error. If these methods are within a single package, this is really easy to fix. You can just dispatch on, you can add an extra method which dispatches on the intersection of those two interfaces. Where the problems really arise is if you have different methods from different third-party packages. However, my gut feeling is that it's not going to be as much of an issue as some people might be afraid. And I'll kind of walk through why I think that's the case. So it's helpful to think about two main categories of methods. We got required methods and provided methods. So the required methods are the methods that are required by an interface. So those methods must be implemented in order to implement the interface. And those methods will typically have dozens of implementations all across the ecosystem. And they usually dispatch on concrete types. So they don't have ambiguities because they're dispatching on concrete types. So the other category of methods then is provided methods. These are typically very generic functions that are defined in terms of the required methods in one or more interfaces. So they usually dispatch on abstract types, or in our case, interfaces. But they usually only have a handful of specializations. And oftentimes those implementations are defined by the function owner. So there's still no issue with ambiguities because there's only a handful of specializations, and most of them are controlled by the owner of that function, of that provided method. And just to elaborate a little bit more on that subject, here's a more specific example. This is sort of hypothetical. It's not, it's inspired by base, but it's not base, I guess. So we have an iterator interface, and we have, the sized iterator interface. I should be extending the iterator interface. That's a typo. So the iterator interface just has the iterate function, and the sized iterator interface extends the iterator interface with the length function. So the iterate function or method and the length function, those are the required methods for those two interfaces. So there's going to be dozens or hundreds of those implementations throughout the ecosystem, but they're usually on concrete types, and that's okay. So that doesn't really cause issues. And here we have a provided method, which is I called it myCollect just to distinguish it from the base collect, but it's basically the collect function. But I've got two different methods. One dispatches on iterator, one dispatches on sized iterator. But this is a provided method. Usually when you implement an interface, you do it because you want to get these provided methods for free. So you're not going to overload myCollect. Like if I define a new iterator, I'm probably not going to overload collect or myCollect. So I, as the creator of the myCollect provided method, I am in control of both of those methods. There's no issues with ambiguities. So hopefully ambiguities will be uncommon. But we won't really know for sure until we have a little bit more real world data. And we have to see how it works out in the ecosystem. If people start to use this, we need to actually see what happens in real life. Okay, let me go over just some kind of example applications of the package. Going back to the graph type example, this is how we could formulate it in multiple interfaces. Here we've got, once again, this sort of root graph interface. We've got an undirected graph interface and a directed graph interface, which extend to the graph interface just like before. But now we have a separate mutable graph interface, which just extends the base graph interface. So we only have one copy of this mutable graph interface, which is nice. Of course, you'll see there's not actually any multiple inheritance in this hierarchy, but the graph types can implement multiple interfaces, so that's sort of where the multiple inheritance comes in. You've essentially got multiple inheritance going from from the interfaces to the concrete types. So here we've got an undirected graph type that I've implemented that implements both the undirected graph interface and the mutable graph interface. And I've got a directed graph type that implements the directed graph interface and the mutable graph interface. And then I can define an I method, foo, which dispatches on an intersection. So I can define one method that dispatches on the intersection of undirected graph and mutable graph, and I can define another method that dispatches on the intersection of directed graph and mutable graph. So we've kind of solved the issue with the original graph type hierarchy. This is just a very hypothetical slide. I like to think about potential ways of organizing a hierarchy of collection interfaces with the having the additional help of having multiple inheritance. So this is very, very hypothetical, just a sketch, and it's definitely not consistent with base Julia 1.x. So any suggestions are very welcome, but the basic idea you can see here. At the very top, I've actually got a container interface, which just has the methods ltype and in. Then the iterator interface in this hypothetical sketch actually extends the container interface. I have a separate hasLength interface, and then a collection interface which extends hasLength and iterator, and it also adds this isEmpty method. So this collection interface is really for immutable collections. If you want a mutable collection, you need to add a few more methods to your interface. So you extend collection to mutable collection with some methods to work with mutability like add, remove, and empty. You also might want to add some other things to the collection interface like getIndex. So we have a sequence interface. This is immutable sequence. The sequence interface is for immutable sequences. So if you want a mutable sequence, then you extend that interface even further to the mutable sequence interface, which adds the setIndex, insert, and delete methods. You could also extend collection to a dequeue with push first, pop first, and push and pop. And in this little code box here, you can kind of just see that, a set, like if you implement a set, it's probably going to implement the mutable collection interface. If you implement a tuple, that would be the sequence interface. Of course, if you implement the dequeue, it would implement the dequeue interface. And if you implement the vector similar to what we have in base Julia, that would implement the mutable sequence and the dequeue interfaces. I also have another example up here. Of course, you can create an alias if you want to. You can create an alias to a interface intersection. So I have an alias for iterator and hasLength, which I call sized iterator. This is all just very hypothetical brainstorming. It would be cool if we could have something like this, but it definitely needs a lot of work. And as it's phrased right now, it's not really consistent with 1.x anyways. So that's about it. I think that abstract multiple inheritance is a really powerful tool for expressing interfaces. It could potentially, of course, have some downsides with ambiguities. But we won't really know for sure until, I mean, as I said in the talk, I think it won't be as bad as some people are afraid it will be. But we won't really know until we try it out in the ecosystem.
Hi, I really enjoyed the talk. Thank you. Can you talk a little bit more about how iMethod is implemented? In particular, how you would handle a mutual ambiguity between normal dispatch and iMethod dispatch?
Yeah. Let's go back to that slide. Oops. Okay. Well, so first of all, you can't really combine type dispatch and interface dispatch in the same argument. They have to be in separate arguments. So one argument can dispatch on types, another argument can dispatch on interfaces. And then the way that works is that first it actually dispatches on types, and it treats the interface arguments as any. And then it'll dispatch on the interfaces. So that has at least one consequence, which is if you can, I've been pretty careful about overriding methods. So like if you define like a foo of x, which just dispatches on any, and then you define foo of x, which dispatches on an interface A, that second definition will overwrite the first one because a foo of x, which dispatches on any, from the type perspective is equivalent to a dispatching on an any. Sorry, foo of x, which dispatches on A, is equivalent to foo of x, which dispatches on any. So it overwrites the previous definition. So I've tried to be careful about that kind of thing.
Hi, thank you very much for the talk. Like, can you go back to the slides 21, please? I have a question. Like, you've been discussing about like inheritance of interfaces, but what about the variables? In that case here, graph define the variable vertices. But then like the sub-classes, the sub-types, like they don't have vertices because you cannot inherit variables. And I think this is something like maybe Julia could be, can do better. That you cannot create a subtype that will, a substruct that will inherit the struct variables, the parents. In that case, like how can you make these vertices in graph accessible in the subtypes? It's not clear to me.
Sorry, not sure if I totally follow the question, but so these are methods. So the graph is the interface, and then
yeah, but vertices, this is a variable, right?
Vertices?
Yeah.
It's a required method of the graph interface. So these are interface extensions, which mean that they add on to the interfaces that they extend. So the undirected graph interface includes neighbors and edges plus the method vertices. So if you want to implement an undirected graph, you have to implement a neighbors method, an edges method, and a vertices method.
Yeah, okay, but I mean, what you're saying is that we could have like efficient multiple interfaces, like useful multiple interfaces, without inheriting variables, and that looks weird to me. I don't know. I would be happy to discuss that further.
Yeah, I'm still not sure I totally understand your question.
Well, I mean, if you have like a point type that has an x and y, and you have a color point that just want to add color to a point.
Yep.
How do you do that if you can't inherit variables?
Well, so there's no concrete inheritance here. Just like in regular Julia, concrete types are final. These are simply interfaces that represent inherited behavior. So each individual graph type is still going to have to implement its own methods. Like, these two graphs down here, my undirected graph and my directed graph, they have totally separate implementations. You have a struct with whatever fields you want, but as long as each of them implements these methods, then you're good.
How, separating from the dispatch between types and interfaces, how does this actually implement interfaces Like, and how do you do dispatch on those?
How you mean like how does dispatch work under the hood kind of?
Yeah.
Well,
Not be enough time.
yeah, it's kind of a long question, but basically, when these various macros are overloading, or they actually redefine some functions which return tuples of singleton types, and those singleton types are used within the dispatch logic. So everything happens basically at the type level, or kind of like that. It's a long question.
We are out of time for questions, but could we have one more round of applause for our speaker? Thank you very much. Our next speaker will set up and proceed shortly. Really good job. Thank you.
And this air plug, my battery's going low.
There should be somewhere. There's one right here behind you.
Okay, that's not gonna.
Port space.
That's. Yeah, this isn't gonna reach. Okay. Oh, there's one right there. All right, that works. All right, thank you. That's just a double. Yeah. Alrighty.
Go ahead.
Yeah, so welcome to the, Applications in SciML session. We're going to have a lot of speakers, and we're starting with a very interesting speaker. It's Dr. Chris Rakakis, and I am right here. All right, so I think that this is going to be an interesting talk because this is a talk that's, it's kind of almost more of a PSA, public service announcement to say, a lot of you have been doing a lot of things wrong, including me, because our tutorials tell you to do the wrong thing. But I think that the right thing to do is to kind of give you an explanation why, and then as a community try to come up with the right ways to correct ourselves, right? And so this is all about fast and robust least squares curve fitting in Julia, right? And so it's a question of, we do this a lot. In fact, a lot of you have probably written down least squares and optimized least squares, and I'll tell you that every single one of you in this room have probably done it wrong, and my tutorials also do this wrong. And I want to tell you why. So basically, if you're just gonna cut off from the YouTube video right now, well, you're gonna miss a lot of really great jokes, right? But the other thing is that you will. And what's the TLDR to take away? You probably should start using curvefit.jl. We want to start deprecating these tools, least squares fit.jl, optim, and in optimization and optim.jl, you probably don't actually want to use an optimizer if you have a least squares problem. And you might go, okay, well, I've been using an optimization, nonlinear optimization tool for least squares for a long time, and that's kind of the point of this talk, right? And so the TL, if you read a little bit, you should probably be using something inside of nonlinearsolve.jl, which is called nonlinear least squares problem, instead of an optimizer. And if you haven't heard about that existing, well, that's the point of this talk. So let's set the stage. What are we actually trying to do? Well, let's say let's just take one of these problems, right? You just have an X, right? So which is an input, and you have a Y, which is an output, and you specify some model. So we just say, f of X with some parameters spits out some values, and those values are supposed to be Y, right? This is your standard, I want to fit a curve to data, right? So the curve fit problem is general, right? But one way that we can de-general it a little bit is to say, I'm going to choose a loss function. And what loss function do we want to choose for what we call a good set of parameters? Can anyone guess? Least squares. Oh, we always do this, right? Okay, we don't always do this. You can generally do something different. And so the optimization tools are set up to be able to, you give me a cost function that could be any possible function in the world, and I will try to find that the optimum for that, right? But we generally don't do any possible function in the world. We do that function, right? We say, okay, we want to find the difference between our data and our model, and we're going to take the square of all these, and we're going to sum all these together, and we want to find the least square solution, right? So the first thing that you should realize is that we're taking this problem that is actually really specific, right? And we're going to be throwing it to something that is completely general. You must lose something, right? So, okay, so we could call an optimizer. This is what it looks like. And if you write your code like this today, that means, yay, you're following our tutorials and you're doing the wrong thing, right? So you call optimization.jl and you choose an optimizer, optimization optim. Okay, BFGS method. You define your model, you put it inside your cost function, and then you tell it to use some automatic differentiation and BFGS, and boom, you're good, right? So there you go. What's wrong with that? Well, let's talk about what it's actually doing here, right? So we're trying to find the minimum of some cost function, right? So we're trying to minimize, some CFP. And how are we going to do that? Well, we know that we have the minimum when you have the derivative equal to 0, right? Let's go back to Calculus 101. If you haven't taken Calculus 101, just step right out of this room, right? So where the gradient's equal to 0, this is where we have the optima or minima, or it's just one of the local minima. It's a necessary condition, not sufficient. Like we all know this, but we always say, oh, whatever, that's for mathematicians. We do machine learning, so we're just going to go to that optima, right? So, okay. We didn't do, how do we actually do this? Well, we're going to use a Newton method, right? We want to find where the gradient is equal to 0. This is a function, so we define a function. G of P is the function which is the gradient of our cost with respect to P, and where the gradient of our cost is equal to 0, that is how we get a minimum. And then we do have Newton iterations, right? And so we go, optimization needs to use Hessians, right? Why does optimization use Hessians? Well, because we're doing a Newton iteration. A Newton iteration needs the Jacobian. But what function are we actually doing the Newton iteration on? The gradient. The Jacobian of the gradient is another name for the Hessian, right? So we need second derivatives. And so we start saying, what are some methods that can approximate second derivatives? BFGS is a quasi-Newton method that makes it that way you don't have to calculate the Hessian. So maybe that's a little bit better, but you lose quadratic convergence and all this stuff that's going on, right? But is any of this even necessary? Right? Let's look at this again. Here's our cost function, right? We have a function in the middle there, residual of P, right? R of P, which is the residual of how far away we are from the data, which is f of x, minus y. I've just rewritten this, right? So our cost function is the sum of squares of our residuals, right? Here's a lemma. The gradient of our cost function is 2 times the residual plus, this is just chain rule, right? Proof is left as a homework exercise. And then class, you will also be graded on with 50% of your grade to prove that if this is your function, that if the residual of everything is equal to 0, then the gradient of the cost function is equal to 0, right? So if your data is going through all of your points, then your difference between your point and your model is always 0, and so therefore the gradient of your cost function is 0, right? This is actually why we chose the cost function in the first place. But does anyone notice something interesting about this? Notice what we're doing. We want to take the gradient of our cost function and we want to make it equal to 0. And then we're going to do a Newton method to start causing that to go towards 0, right? The gradient of our cost function is the model minus the data, which is something that we actually just wrote down. So what we're doing in this code is we're saying, hey, model minus the data. This is the thing that we care about. We're then going to square it and put a summation over it. And then inside of the optimizer, we're going to do reverse monotomic differentiation on the gradient to get that piece in the middle of the code again, right? Because remember, the gradient of our cost function is really just returning, that function in there, like model minus y, right? And so the gradient function in the optimizer is just going to do that, and then we're going to calculate the derivative on top of that, right? So why are we wrapping it in a higher level function just for automatic differentiation to try to get rid of that? I mean, it's just adding more overhead. It's just adding more. We're only taking a second derivative because we put something on top of it, right? So we really shouldn't be doing this, right? So let's take a step back, one step back, and just say, is there a way to be doing nonlinear least squares in a way that's not just looking at it as an optimization problem? And the right way to do this is just go back. Well, what's the intention of a Newton method in the first place? Newton's method is just, you can write it down in math and whatnot, but it's actually a very simple idea. I have a function that I want to go to 0. I'm going to approximate that function by a linear function, right? How do I approximate it by a linear function? It's just the derivative times the current value, right? So I approximate my function as linear, and I just say, hey, if my function was linear, where would it be 0? And I walk to that, and I approximate my function as linear again. And I say, well, if my function is linear, where would it be 0, right? So it's a method where we say, hey, look, I want to find the 0 of a function by assuming my function is linear and taking steps, right? So what we've done is we said, okay, I want to find out where data model minus data is equal to 0. So what I do is I stick it inside of a larger function that has a cost, and then what I'm going to do is I'm going to do reverse mode automatic differentiation to get rid of that larger function on top of it again, and I'm going to apply Newton's method to find out where that inner function is equal to 0, right? And I will do that so that way I will solve a nonlinear least squares problem. But why not just change the intuition of Newton's method, right? Newton's method says you take a function, you make it simpler, and you solve the problem you want to solve, and then you take let's do the same thing except for least squares, right? So we just say, okay, what I want to do is I want to take my function, I approximate it as linear, and I find out where for this linear function I will solve the least squares problem, and I walk to there, and I take my function, and I approximate it as linear, and I say, where for the inputs of this function do I solve the least squares problem? And I walk to there, and do that. It's like Newton's method. It's the same exact idea, except you're not doing successive 0 solving. You're doing successive nonlinear least squares solving, or linear least squares solving, right? Because now it's a linear function, then you get to do linear least squares. This actually has a name, right? Nothing that I'm saying here is unknown to numerical analysts. It's called the Gauss-Newton method, right? So if you look it up on Wikipedia, you go, oh, hey, look, there's actually an algorithm for this. The Gauss-Newton algorithm looks like this, right? And you can directly do this Newton steps. And so the key here, so this is what it looks like on Wikipedia, and you just go, okay, wow, what an algorithm, right? And so then you see people actually go and implement this in numerical packages, and they implement it just like the equations are written down. And yeah, I see the numerical analysts be like, oh my God, did you actually implement it like this? Because the way that it's even written down, if you look it up online, is how you never want to implement it. Because, that Jacobian times Jacobian, right? So let's actually look at what's going on here, right? So basically in the steps, what you're doing is you say, I linearize my function, and then I do a least squares fit. One way to do linear least squares fit is to just take to take your matrix, multiply it by the transpose, and then do a factorization. That is a linear least squares fit. So you're doing exactly what I said intuition-wise, just at every step. So now what we've done is we're changing our function. Now we're the Jacobian that we're looking at here is just the Jacobian of that residual function r. So we're just saying, okay, we have r. I now directly use its Jacobian, no second derivatives. I just directly use its Jacobian, and I follow what Wikipedia says. And I'm still doing the wrong thing, because if I follow what Wikipedia says, then I'm doing matrix transpose times matrix, which doubles my condition number. And doubling your condition number means that you're going to have really bad numerical properties. So when I say at the beginning, like, I'm not trying to throw shade on other packages, but this is the kind of thing that I'll see in a commonly used package like least square fit.jl. This is why it won't necessarily work so well if you have these, matrices that are near singular or from stiff equations and such, because this is a numerical numerical problem that will show up in there, right? So you know, so what tends to happen here is you're either using a package that has some numerical issues in it, or you're using a nonlinear optimizer and you're taking second derivatives when there's algorithms that will do this with only first derivative. Like, what do we do differently here, right? Well, the key is that if you actually just look up a very basic, you know, numerical analysis fact, it turns out that the QR decomposition is a thing where if you have a matrix and you use it inside of a backslash operation, like a least squares, you know, a linear solve operation, it will naturally give you the linear least squares fit. I mean, it's literally there right at the top of the Wikipedia page, right? This is a well-known fact. And so instead of doing a prime A backslash B, if you just did QR of A backslash B, then you'll get something that will solve the linear least squares problem, and it will be the optimized version that Bloss and Julia and everything has already defined for you. And that's what you put that inside of there, but there's nothing that actually writes this online, right? And and also there's all this other stuff that happens when you have the QR factorization. It's doing these house order reflections and making sure that it's very numerically stable. Go see John Ursul's talk from yesterday about there's a lot of issues with the LU factorization, but actually we can actually prove that QR factorization doesn't have these issues with house order reflections. So it's actually a very stable algorithm, whereas LU factorization or Cholesky on this is a very unstable algorithm, right? So this is good. This QR is actually really good. So what we really want to do is you want to say, hey, look, take a library that is already doing Newton methods, and you want to do the exact same iteration, but where you have that LU factorization, swap in a QR factorization, and just by that sleight of hand, now you are solving nonlinear least squares problems really well, numerically efficiently, robustly, and everything. And then also the same line tricks apply. Line search tricks apply too, right? So when you do Newton's method, you go Newton method with line search, Newton method with trust region, Well, you do all of that, and you just have a QR factorization, and now it's the good version for nonlinear least squares. In fact, you could even start to write down that Levenberg-Marquette is a Gauss-Newton method with the line search, right? So when you say, oh, Levenberg-Marquette is a method for these things, no, it's literally just a Newton method with a line search where you just swap in a QR factorization, right? And so in the nonlinear solve.jl paper, we go into a lot of detail exactly about these equivalences between what people have found in the nonlinear least squares problems and all these other things, right? So then the thing is, you just say, okay, well, if we figure this out, then let's put it all, let's put this all in a repo, and let's do it right, document it, and boom, we're really good, and everyone's doing the right thing, right? But you might start to see what the issue is here, right? So, okay, how do you actually implement these types of Gauss, Newton, and beyond methods? So Levenberg-Marquette with trust regions and these geodesic accelerations. Well, it's exactly the same infrastructure as the methods for solving nonlinear solve, except you're swapping out to a QR factorization. So the right place to put that is in nonlinearsolve.jl, right? Who here knew that you can go find the tool for solving a nonlinear least squares problem in nonlinearsolve.jl? Let me see from the audience. Okay, there's some people in here, but yeah, a good portion of the audience does not know that that's the right place to look, because it's not a library for optimization, but the most common optimization problem that you do is a least squares fit, and the tool that you want to use for this is not inside the optimization library. But you understand now why it's not there, right? Like, it's infrastructurally exactly the same thing as the nonlinear solver. And so it needs to be there code-wise, but this is where things are kind of funky, right? This is where I can't blame you. I got to blame myself a little bit. So, okay, and it's actually working really well, right? We actually had the paper on nonlinear solve. I think it was recently accepted. I put a question mark because my student who was leading this effort is actually currently giving another talk right now, and so I don't know whether it was fully accepted or we had to do like the minorest of revisions. But yeah, like, our claims that we have this to be super robust, right? It's working in cases where, sundials and minpack are failing, right? So they'll diverge on a lot of these problems where we converge. It has a lot of, default optimizer choices, a lot of trust region methods and line search methods that are really well tuned. It's highly performant, right? So we're able to put this in this package and we say, hey, look, all of the things that you get from nonlinear solve, all that effort actually applies to least squares fitting too. It's all in there. And all you have to do is you have to call nonlinearsolve.jl nonlinear least squares problem, and it solves very crucial issues, right? So one thing that it does is that if you have in a nonlinear system, so you normally think about a nonlinear system, you say, hey, I have 3 equations, 3 unknowns, solve it. One of the nice things that you get is that if you use a QR factorization, you don't need a square matrix anymore. And so underconditioned and overconditioned problems are actually just solved. So if you had a nonlinear problem and you didn't, if you had a nonlinear set of equations, you had more equations than your number of unknowns, if you just change from nonlinear problem to nonlinear least squares problem, that's actually the right way to solve this. And it solves, it's also, if you have a nonlinear problem and you have a Jacobian singularity, right? If your Jacobian is not invertible, it turns out that you can actually solve that too using nonlinear least squares problem because this algorithm is robust to that. And, it also solves nonlinear least squares problems, like an actual optimization problem. But it's called nonlinear least squares problem, so I would guess that most people in the audience would not. If you ran into a problem where you saw that your nonlinear solve was not converging because you had a singularity, you probably would have not thought, oh, let's go choose nonlinear least squares problem. That's the solution right here. It is the solution, but this piece baked in here that it says, hey, look, I am a thing to solve a nonlinear optimization problem. I am also your thing to do when you have an overconditioned or underconditioned problem. I am also the thing to do if you need more numerical stability. I am just name myself after an optimization problem. And so, there it is in there, right? So there's nonlinear least squares problem baked deep inside of the nonlinear solve documentation, and then there's this, there's even a page that's called nonlinear least squares solvers, and you'll see like, oh, these solvers are named in there, right? There's your Gauss-Newton, there's your Levenberg-Marquette, there's the trust region. Well, trust region is actually just the same name of the method on nonlinear solve, right? Again, it's just we just changed the factorization inside of this case. It ends up being the one that we default to, and all this stuff is in there. And there's even one tutorial in there that says, hey, look, a right way to do a least squares fit for parameterizing an ODE is actually to call nonlinear least squares problem. If you look inside of the nonlinear solve documentation, it's there. If you go to all the other examples, we always call optim and everything. Oops, we haven't updated everything, but it's in there. So what I'm really alluding to is that there has been kind of an ecosystem failure here. I will completely admit that a lot more people should be using this nonlinear least squares problem, right? A lot of people who will be going through this this session, right? There will be this scientific machine learning session where most people will have a loss function that's a least squares loss function, and you will see the code that they show there, and none of them will show you that they're using a nonlinear least squares problem. They will all be calling a nonlinear optimizer, right? So that's an ecosystem failure. That's not a failure on your part. That's a failure on my part, because I've been just told you exactly why. Now that all of you know that this is the case, let's start to diagnose what's the issue here, right? So if you wanted to solve first of all, if you wanted to solve a least squares optimization problem, would you look at the library called optimization.jl, or would you look at nonlinearsolve.jl? There's a discoverability problem. That's very clear, right? But it's also now should be understood why this piece exists inside of nonlinearsolve.jl, right? It's a code structure thing. It is not a thing about usage. And if you wanted to solve an overdetermined or underdetermined problem, would you understand that nonlinear least squares problem is the thing to do? Right? Why is putting least squares the thing that you'd want to, like, for some people who might go, oh, overdetermined, the standard way to think about it is the least squares, but it's not really in the naming, so there's a discoverability issue. And if you had a singular Jacobian, yeah, would least squares be the first thing that you look at? I actually didn't realize that we already had this thing solved until last month. And so then I actually changed the nonlinear solve.jl default solver so that way it will do this trick as part of it. Only last month, because it's when I realized, oh, we actually already have an algorithm that handles this case. So yeah, you probably wouldn't go looking for nonlinear least squares problem as the solution to these problems. So what can we do, right? There's some potential solutions here. And again, I think that this is a difficult problem because nonlinear least squares problem lives baked inside of nonlinearsolve.jl for a reason, right? So what are some things that we can or should be trying to start doing, right? Well, the first thing is to try to educate people about, hey, look, this thing exists, you should use it, and this talk is literally that start. In fact, I was talking with a Julia user at the time when I was, sitting on this island in this nice workshop, and we're talking, and he's like, oh, I'm having issues fitting this least squares problem. And I said, why are you doing this with optimization.jl? Like, just use non-linear least squares problem, and boom, it fixed up this problem immediately. And he's like, how come you haven't told anyone about this? And the RFP for JuliaCon went up, and I said, okay, I'm going to have to commit myself to telling people about this. So that's how this talk happened, right? It was in the long list of talks, but I was kind of like, I was just like, you have to do this. All right, cool. But, now that you know about this, you will have to go police everyone else that you know and say, oh, how are you solving your nonlinear least squares problem? Have you ever heard of Gauss-Newton? I mean, it sounds like you don't know what you're doing, right? So part of it is just this network effect of just telling people, hey, here's this story. It's really interesting. It's really cool. A lot of people who are not in numerical analysis never heard of it. Now that you know the story, go spread the word and tell people, right? But there's other things that we need to do, right? We need to make it so that way symbolic tooling like Modeling Toolkit more naturally pushes you into using these tools, right? Right now, I'll show you in a second that in some cases it helps you, in some cases it pushes you away. And we also need to make the even higher level tools, right? Maybe we need to have a tool, and so we actually started to have a tool called curvefit.jl, where if you want to just fit a curve, it will just do the right thing for you. And for most people, you don't need to know anything about how it's solving, right? And so we just need another level of abstraction. And that level of abstraction needs a bit more work, but I'll show this in a second. But we also need to somehow document this and make this more clear. I don't think that I have a complete solution for this, right? Nonlinearsolve.jl defining nonlinear least squares problem is kind of weird. So some ideas that I've had is, what if we just create a nonlinear least squares.jl thing that has no code, and it just exists there to be a documentation for how to solve nonlinear least squares problems, just so that way we can put it in the documentation and Google finds it better, right? So there's all these different ideas that I've had, but I think that, again, the code is already here. It's already optimized. It works really well. We've tested it and everything, but we need to figure out, there is a true discoverability problem, and we need to do something about it. So I want to show you this a little bit. So if you go to Modeling Toolkit and you define a problem, and you have 2 equations with 3 unknowns, this is solvable, right? By a nonlinear least squares problem. By default, if you do everything in the documentation that you would have done for the nonlinear system, it'll throw you an error and say the system's unbalanced because you don't have enough equations for your number of variables. You can get around this. You can say, hey, look, my fully determined equals false, and the compiler will no longer error about this. You then do a nonlinear least squares problem, which is something that can solve underdetermined problems. You call solve, and it works. So it's all in there, but there's a discoverability problem, right? But there's a trade-off problem too, right? Because I think some of you will be like, oh, but I want my tool to tell me when I'm missing an equation because I want to make sure I have a determined system, right? And so there's a balance between different use cases of this makes it much harder for people to find the right way to solve the least squares problem in this case, but a lot of people want to know, like, hey, I probably misspecified my model if I have 2 equations with 3 unknowns. So how do we actually balance between this? I think we need better error messages, better documentation of this and such. But it's not so easy as just saying, hey, just always do it like this, right? It's legitimately difficult. But one of the things that we do, though, is if you give a differential algebraic equation, right? So here's a differential algebraic equation, and then it needs actually 2 initial conditions and 1 parameter definition in order to be well defined. And so, boom, in the documentation, we first show that if you do it that way, it's fully determined, and it will solve this. And it will solve this via a nonlinear problem. But if you give it too many conditions, it'll tell you that the initialization is overdetermined, and it'll still solve this, right? How does this solve this? If you look at what it's doing in the code, the initialization problem is a nonlinear least squares problem. It's doing exactly what I showed in the first part, right? And if you give it too few initial conditions, it will also solve this using a nonlinear least squares problem as I showed in the first part, right? So we're starting to do this automation, but even then, some people will say, oh, I want to know when my equations aren't wrong, so we have a warning right there, but some people want that warning to be an error by default instead. And there's a war between different factions that have different wants and needs. And so I think that, again, I think the best thing to try to really find a real solution here is to educate people and have a real conversation of what does the community want and need. And lastly, right, we're trying to put this together where, so this is for just solving systems of equations, which, again, is not even in the name for nonlinear least squares problem, but it's probably one of the biggest use cases right now. The other one is I actually want to fit curves to data via nonlinear least squares. And so what we did is said, okay, let's help bring back this library. There's a curvefit.jl that was in the ecosystem. It didn't have all that much. We kind of took it into SciML, with the blessings of the author. We've updated it, and the documentation documentation just went online about 2 minutes ago. As I was walking up there, that's what you saw me punching. And it's very simple. You give it the data, you give it some initial parameters, nonlinear curve fit problem, boom, you solve it. It looks just like other SciML libraries, except this is now the optimized way to do it, kind of, right? Again, we need a lot more documentation. It only has the out-of-place form right now. We need the in-place form. We also want to make it so that way other things that you might want in the nonlinear least squares case are, for example, statistical information about confidence intervals. This is a good place to put that kind of Hessian calculation information for those who want that. We should put a switch in there for speed versus robustness, right? Because actually using that Jacobian prime Jacobian is actually faster if you mix that with a Cholesky factorization. So we need to basically give it a switch of do you want it robust and slower, or do you want it faster and less numerically robust, right? So it's just a high level switch, fast mode equals true false. Instead of so that way you don't need to know all this details about how the algorithm works. We need a few tutorials to make it more accessible. And one of the other things is that people need to know about this library, hence this talk, and we need to update other SciML examples to use it, because right now all of our tutorials for how do you do things like universal differential equation fitting and all of that uses optimization.jl, when a lot of those tutorials should be using these other tools. So thank you. Hopefully this is a PSA for how you should be changing a lot of the code that you've already written. So thank you very much.
So thanks, Chris. I just want to say I'm doing my part. So if you're teaching your students using fncbook.com, it's the last section of chapter 4. It explains nonlinear least squares exactly this way. And because I use backslash in my Levenberg-Marquardt code, it's the same code. It's not even changing the factorization. So
amazing.
So optimization.jl already has a ton of back-end solvers that it can use. Why not just add nonlinear solve as a possible?
Great question. Yeah, I forgot to address that. So the issue is that this kind of flow, this algorithm and everything only works for nonlinear least squares problems. So what we'd have to do is optimization.jl wants you to give it a cost function. So what we'd have to do is we'd have to discover, hey, from your cost function, if you calculate the gradient of your cost function, right, the gradient of that cost function needs to have a given form, or we'd have to compiler discover, hey, this is actually a nonlinear least squares problem. And so therefore, here's an algorithm. This algorithm is appropriate for it, right? So we need you to give us. So the difference between the optimizer and the nonlinear least squares interface, right, is that the optimizer wants C of P. It wants the cost function to be, I give you P, you give me a scalar, right? The nonlinear least squares method wants to know what is the residual of all the parts, because it's going to want to take the Jacobian of that function. So it wants you to give it R of P. Right? R of P is related to C of P, but optimization.jl in its interface does not know what R of P is, right? It can kind of infer kind of what it is if you take if you do enzyme on your function, but again, it's not actually giving you, there's an extra piece in the chain rule in there and such, right? The yada, yada, yada. But so the interface is wrong. The thing is, if you give in a cost function, then you've already lost that piece of information that, hey, look, this is not a general cost function. This is a nonlinear least squares problem. And the linear least squares problem has a good solution, so therefore I want to specialize on this, right? It's missing this higher level mathematical intuition and information, and so yeah, there's a really good question of can we mix this with the optimization library? Could there be a compiler pass that actually discovers and proves, hey, look, this is actually a least squares problem, right? There's the compiler passes that we've done for things like finding sparsity patterns, and there's things like automatic differentiation. Is there such a data flow compiler algorithm that proves that something is a least squares problem? I think it could be possible, but right now we don't have anything to do that. So the user has to know to give us that information rather than giving us a general cost function. I think this then leads to the user interface pieces. But now that you know that this problem is there, hopefully you'll give me that RFP instead.
Thanks for the talk, Chris. Maybe I missed, but how do you do robust curve fitting, like with L1 loss or something?
Yeah, so there's a lot of nice stuff about that. So basically, the same intuition applies, right? Where you can just say, okay, I can do Newton's method, right? Newton's method is solve go to a 0 each time, right? And then Gauss-Newton is you go to the linear least squares fit each time, right? You can do the same exact idea. Okay, I want to linearize my problem. I want to do a linear LOI1 regularized call every single time, right?
I mean,
And
is it in curve fit or?
It's not in curve fit, but I'm telling you how to do it so that way you can add it and give a PR, right? And so then the key is like, is there a tooling out there that can do this? I don't think that's actually implemented in Julia, but there are some proofs out there that show that if you use a truncated SVD, there's a way to use the truncated, similar to how QR factorization gives you the linear least squares fit. A truncated SVD in the right form gives you the Tychonoff regularized least squares fit, right? And so this generalization of I want to have L1 or L2 regularization, if you swap out this QR with a specific form of the truncated SVD, it will actually give you that, and then the same algorithm will apply. We have not implemented that because we're missing the right truncated SVD things inside of the library, but it would be a very fantastic GSOC project or otherwise to actually do that, because that would be a really nice way to do regularized
Okay, thank you. I guess I just misunderstood the word robust in the title. And also, is it just the local optimization methods, or so in optimization.gl you have global fitting as well?
Yeah, so this is all local. This is all local. Yeah, so we're only looking at local here. So let me explain a little bit on the robustness there. The robustness comes from the fact that there's this whole aspect about doing the linear fit correctly, right? Doing this with QR. You'd also get that for the regularized form if you did this with a truncated SVD, because the truncated SVD is a very numerically stable algorithm for that, right? But then the other thing that comes into play too is that once you're in this flow, you get all the different trust region methods and the line search methods, geodesic acceleration. And these pieces give a lot of that too, right? So if you did this exact same algorithm, but you swapped in the truncated SVD in the right spot, then you would have the line search trust region version of a regularized least squares operation. And I've never actually seen C or Fortran. I'm not sure if there is a code out there that does this, but it'd be probably the best way to implement it. And so someone should do this, but the infrastructure's right there. But yeah, we need to do that part.
On the interface subject, could we have just a L2 optimization problem?
Yeah, we could just have an L2 optimization problem, and then we document it in the optimization.jl library, because that kind of, is starting to get people like, hey, look, I'm looking at optimization.jl, and I just happen to find that this thing, that L2, or least squares optimized is in there. Okay, cool, right? And maybe it just aliases over to the same problem, right? Like the user doesn't need to know that we're actually just playing a trick on them, right? That's the thing. It's like getting the information in the right spot. We've got this wrong right now, but if it's just a name change that does it, maybe that's the right solution.
Thanks. That was a really cool talk. There is a package called gmodelfit. I don't know if you've heard of it, but it's kind of like lmfit, but in Julia. So lmfit is like a more high-level library for doing curve fitting. And gmodelfit already supports nonlinear solve and least square fit.jl and one other thing whose name I forget. Maybe it would be cool to use that as like an interface to different libraries and add support for curvefit.jl.
Yeah, I had not known about that. So thank you about that. Maybe that's maybe that is the right way to go with the high-level library. We're just trying to find new solutions. So definitely send that to me, and I'll look into that. I'll probably want to collaborate with the author if they're already starting to do this.
Thanks. Hi, Chris. I was wondering when I guess these parts of SciML would be integrated with the reactant, so we could just offload it to the GPU without thinking
Reactant
twice.
already works with this. Avik
Awesome.
did a test, yeah. So, I mean, yeah, you could trace through these just fine. Perfect. I will say that one thing that we need to do throughout a lot of SciML, this is kind of going down a deeper topic, we do want to go through a lot of these tools, and whenever there's a while loop, make sure that we do @JIT on that, or to be able to capture like, hey, look, tell Reactant to keep this loop structure intact, right? So we can get more optimized code generated with Reactant, right? And so we're working with Billy. I mean, Billy and Avik are not two people who are disconnected from the SciML group. Like Avik is literally one of the students I talk to every single day. day, right? So like we're really trying to get the right integration here. And so yeah, I'm hoping that basically the tutorial should start telling people to use React Intent probably by December or so. Because that's one of the other things that it solves is it handles a lot of the allocation problems that people have with array allocations. And rather than me helping tell people how to fix your code, I'd rather just have a tool do that for 90% of the cases. So yeah, perfect. We're doing that.
All right, thank you for the questions. Can we get one more round of applause for our speaker? And that's it for now. I hope you all enjoy the lunch break.
Yep. I think there should be a correction. 11 mapper doesn't have a line search. It's just a task-driven variant of iteration. I have implemented this line algorithm side.
You can represent it as a line search, Gaussian.
You can add it, but it's not part of the core algorithm. Yes, it only basically it adds unit matrix scaled by a number to Jacobian times transpose Jacobian, and that's all. It doesn't. It still makes one step per iteration of the loop.
Yes.
Sorry? Isn't it starting now? Yeah. We have 10 minutes. Half an hour. Okay. Hello. My name is Sebastian, and I will be talking today about acausal model augmentation with neural networks. So first, let's unpack the title a bit. What is the acausal part? So in acausal modeling, we want to represent the dynamics of the system as collections of components and connections between them, instead of just working directly with a potentially large system of differential algebraic equations. The large system of differential algebraic equations is still there, and it's still being automatically built, but the main point is that we don't start with that. We don't write that by hand. This can be done in Julia with Modeling Toolkit, and there's been several talks about Modeling Toolkit already. And the important part here is that we can visualize these connections and components in a graphical manner with block diagrams. And this is the ability to visualize our system in this way instead of just looking at the equation can provide a lot of physical insight into understanding how the system works and how it behaves. And just as an example of like how does this look like, here we have a simple thermal system where we have some heat source that heats up a system of a plate and some a pot. So you're making tea, for example. And this is also in contact with the air around it. And now we can either look at this, or we could also represent this graphically. And this is maybe a bit easier to understand, and it's also easier to visualize, and more importantly, easier to debug, because when you would write this, you need to connect the things in the right way and to make sure that you connected everything correctly. But this all simplifies to just two ODs. So all of that diagram with multiple components is just governed by these two ODs. And here, when we compile this with MTK, we see that, these first two equations, they essentially, it's just Modeling Toolkit telling us that this is the shortcut for the derivative for the time and so on. So we want to expand this to see what actually happens in there. And we can see that this can get a bit complicated because it includes all the interactions in the system. And now, what about the model augmentation part, right? So when doing UDs, usually we've seen this example of the Lorentz equations everywhere with how would you do UDs. You have your system of differential equations, and you add a term from the neural network. Or you can do more complicated things if you just don't want to just add it. But the main point is that here we are working directly at the level of differential equations. But we just saw before that we also have in this representation, we have the block diagram, we have the components, we can visualize that. But if we want to do model augmentation and UDEs, we don't want to lose this ability of still being able to visualize how the system interacts, where the neural network is, and not just something that would be shoved down somewhere in this equation. And what if we can represent the neural network as a first-class citizen in this system? And this is what Modeling Toolkit Neural Nets does. So it's a package that allows you to symbolically represent a neural network as a component in your system. And there's two versions of the API. You can either use a block as a system, or you can use callable parameters, but this talk is focusing on the block interface and how you can use it as a system. And the implementation of this is actually quite simple in the package. We just have the parameters of the neural network, and we just call lux to give us what's the output of the neural network given the inputs to the neural network block. So how can we use this? So this neural network block can be viewed as just a black box thing with inputs and outputs. So we just need to connect the right inputs and outputs in our system, and then it will fully integrate with MTK and all the symbolic simplification stuff and everything that MTK does will be performed on with this neural network block being embedded in the system. So we've seen that we have two ways of approaching this model augmentation, either working directly after structural simplification at the system level, and this is what I'm going to call system level UDs, and there's actually a talk right after this one, which I think will go into that if I understood the title correctly, and component-based UDs, where the fact that you are working with components is a fundamental part. You want to be able to enforce constraints on how the neural network interacts with the rest of the system via the block interface and via the, treating it as its own system, which has potentially constraints or has a well-defined interface for interacting with the rest of the system at the block diagram level. Okay, so let's see an example of how we would actually use this. So we are going to start with, again, a thermal system, but we had actually a few slides ago a slightly different thermal system, but we might have forgotten what we've put in there. So let's start with a simpler version where we recall that we had a heat source and something that was heating up, this pot component, and we are going to use neural networks to recover the rest of the system that we forgot about. So when we are building this, the full model has a lot of equations which map to the block diagram, and now we are simplifying it, and we observe here that we just have one equation. This is a simpler system, and it's not just a simpler system because it has less terms in one of the equations. It's a simpler system because we have less states in here. So we will also need to introduce a new state with our neural network. And we can also compare predictions of the system from the first part of the talk with what we have right now. And we see they have a slight difference in their behavior. So the pot is hitting slightly faster in this simplified approach. And we're going to try to find out how we can explain this via a new component. So we would want to add into the system the neural network in sort of this way. We want to put it between the source and this pot element, and it will be connected then with everything. But we cannot just put a neural network in the system because the system works with physical units. It works with heat ports. It needs temperatures. It needs heat capacities. It needs heat flow rate. So the neural network just knows numbers. So we need a specialized component that will be our interface to the thermal domain, essentially, for this particular problem. And we want to see how would we formulate this specialized component that interacts in a physical way with the neural network. Okay, so let's take a closer look. So we have first the neural network, And we see here that you need to specify the number of inputs, the number of outputs, and then the network itself, of course. And this can be any lux.jl neural network. And Modeling Toolkit Neural Nets also offers some simple utility functions for building such neural networks. And one important thing to note here is that this neural network that is created by our utility function has, at the end, it has the last layer such that the weights are multiplied with a very small number, so that initially, when we add this to the system, it doesn't affect much, so that we don't start, I mean, the neural network weights will be random at the beginning. So we need to make sure that this randomness doesn't affect the system too much so that we can start the training from a stable state. What else do we have in this specialized component? We have heat ports. This is how we interact with the rest of the system. That's the physical part on how do we interact with the rest of the system. And now, how does this component work? So this is the interesting part. How would one write such a component in the first place? So the important thing is that when we are working at this level, at the block diagram level, we want our neural network to represent physically meaningful relations. So we need to actually make sense from a physics standpoint when we are building this component. And what do we know from physics about this thermal system? Well, we know that we want a conservative component at steady state. And this means that when the derivative, so here, yeah, the first thing that I wanted to mention, yeah, we have a missing state dimension of the system, so we want to integrate a new state that will be, that is created by this neural network component, and this means that we'll need the derivative of this unknown state will be some function of the neural network output, so that the neural network output gets integrated. And when this derivative is 0, we want the heat flow from port A to be plus the one at port B to be 0, so that we have some conservative, the component is conservative essentially. And another thing that we want is that the neural network works usually with small numbers. Our temperatures are, like we work in Kelvin, so we need to normalize the temperature value such that it's in the range where a neural network can work with it more easily. So this is how we can come up with these equations of how does one go from just the neural network to some physical component that can actually be put in the system. So now let's put everything together, and we see that we get similarly large system here. And if we take a closer look, we can see that, yes, we still have this neural network is somewhere in here, and this is now simplified to just these two equations. So we have a new state as we wanted, and we can now check if this if this simulates correctly in the initial state, so it doesn't blow up initially. This works. So we can continue by training the neural network. Here we are grabbing the neural network parameters, which are just a vector parameter, it's a vector of numbers that we just then update the solution here for. This is using an optimization problem with I should update this to the nonlinear least squares thing, as was mentioned in the previous talk. So yeah, and now we can train this in a two-stage manner. First, we will do some iterations with Adam, and we can see here that the loss is decreasing. And then the last stage, the second stage, we can create a new a new optimization problem where we start from where we stopped with Adam, and then do LBFGS, and this will get our trained neural network. And now let's build a new OD problem and see how well does this fit. This is a very simple system, so our system is very small. The neural network was also very small, and this is now fitting perfectly. And one thing to note here, so we only have if you look at the plot here with the temperatures on the second row, this is the only data that we have that we are using in the loss function. But we need other things in the system to match with what would be expected. In this case, since we started with some synthetic data, we know everything about the correct answer. When you are doing this on a more realistic case, you would not know that, of course. But what I'm trying to show here is that we need to be able to match the neural network outputs to the correct physics, not just to fit the data, because fitting the data can be done even if the neural network outputs are completely different from anything physical. And from this, just by training the neural network to fit the data, that is not enough to ensure that your physical behavior is correct. This is why we have to construct that specialized neural network component such that we embed the correct physics from the structure, and that allows us to be able to match this. I mean, actually worked on several iterations of that specialized component until I got it to be physically correct. And this is, I mean, I could get it to fit, but yeah, the physics was wrong. So it's not enough to just train the neural network. The physics part is also very important. And we can now also evaluate the results and see that our trained UD is perfectly matching the results that we expect from the original system. And what's next? We train the neural network, it does everything. So what can we do next? We actually, now that we have the neural network output, we might want to look at, okay, can we actually represent this symbolically? And yeah, we can use symbolic regression to get from the neural network inputs. So we have the neural network inputs, we have the neural network outputs, and this is just a mapping between two vectors. And we want to search for what symbolic expression can get from the two inputs that we have to the one output that we have. And we actually find something that's interesting, and we see here in one of the results from symbolic regression, we have a difference between the inputs. And this, our inputs were the temperatures. So this, and our outputs was the heat flow. So this, again, makes sense physically because we are computing the heat flow rate from temperatures, and we also have some constants there that represent, I mean, these are parameters that if we were to fit like, I think capacitance, heat capacity, or we would get that. So we have a linear system here. So when we replace those components, they were linear. So again, everything matches what we would expect. One thing that I wanted to mention is that symbolic regression will give us how many candidates we want. So we have, I mean, there is no unique mapping, no unique solution to this mapping. So again, we need some, I mean, this can help us gain more insight, but it's not like it's going to just give you the right answer and that's it. Like, it's not magic. And we see that if we look at the other results here, they are almost the same thing. Like here we subtract a very small number from one of the temperatures, so this is basically 0. Here we, another example is, yeah, here again we just change slightly a bit the numbers here, but the fundamental part is still that we have a difference between these two inputs that's scaled by some constants after. So now that I've gotten to this part, you might have seen talks about dyad, and you might be wondering if there's any relation between this and dyad. And the idea is that with dyad we can represent this in a declarative manner with analysis. So this is an analysis definition for how you could do UDEs, and the idea would be that you don't want to just have to manually go through all the steps. We can formalize all of this and package it in this analysis format so that you can easily go from the block diagram. And if you might have noticed, there were some screenshots of block diagrams that's from dyad actually. And I can also, so they are actually from here. So this is where I took the screenshots from. And here the idea would be that you can go from the block diagram representation to an analysis where, again, you work in the block diagram space. And this helps encode the physics better, and then you can create your own blocks that encode the physics of the problem and do the right constraints from the physical standpoint. And then, yeah, this is upcoming, so this will be available soon. And yeah, if you have any questions about the methodology or about modeling toolkit neural nets, let me know. The modeling toolkit neural nets also has new documentation as of this morning. And this example is also presented here, and we can see everything also in the new modeling toolkit neural nets docs. There was actually also a slightly breaking release for modeling toolkit neural nets very recently to simplify the interface a bit. Not sure if anyone was using MTK neural nets before. It didn't have great documentation. It was like this is starting to be the documentation. And yeah, so modeling toolkit neural nets is from SciML. It's open source, so you can use it. And this is where you would go and learn more about how it works, what are the APIs, and how it can be useful for your own problems. Thank you.
Yeah, so I think Chris is supposed to be chairing this session, but I think he has an overlap, so I will fill in for him. Are there any questions for the speaker?
So just to make sure I heard you correctly, so on that example you gave, the cost function was just on the temperature?
Yeah.
And you mentioned you had to play a little bit with the neural net to get it to be physically accurate. And what was that playing you did? Was it?
So here the important part is, let me see if I can go back to the slides. The playing around was this, how does this component work? So let's, the equations here, you can write the way that the neural network interacts with the rest of the system in many ways. Like, and you can get a lot of variants to fit, but the thing is that you have to think about like what physical constraints on the system. Like one of the important physical constraints was that at steady state, you want the system to be conservative. So there is some physical intuition that gets into building this, and this then constrains the way that the neural network interacts with the rest of the system.
Yeah, just so two quick questions. The first one is any recommendation on how you choose like the neural network, how many layers and things like that?
Yeah.
And the second question that is a bit non-related is, have you had cases where, for example, you would, like the addition of the neural network would add nonlinear systems to your model because you would basically connect?
Yeah, it can happen that this can create a DAE. So that can happen. The question is if you want that to happen or not. In this case, this was a very simple linear system, and I know that I don't want that to happen. But I mean, and actually in version 1 of Modeling Toolkit Neural Nets, which was working with MTK v9, we actually, there was, because of how the equations were ordered in MTK, we would actually always get a DAE because the updates to the neural network was done via an algebraic equations instead of being already embedded in the update. So that was a side effect of how the symbolic system in Modeling Toolkit was interacting, and there were cases in which would give you DAEs or not. So yeah, that's one of the things. And the other one on the recommendations for how many layers and so on. So here, I mean, the thing is that how complex is the missing physics that you are trying to discover with this. So here I had a very simple thing. So I have a very small neural network. You might have seen that it has 4 neurons. Like it's extremely small, but to find something that's described by a line, I mean, it's overkill, right? Like we have 37 numbers instead of just 2 numbers. So even that is very large. But this very much depends on the type of phenomena that you're trying to recover with this method.
Hi, thanks for the amazing talk. I had a quick question. You showed the symbolic expressions that were generated from the symbolic regression.
Yeah.
And gave an idea of how to pick the correct or sort of seemingly correct expression from the available candidates. Are there any guidelines on how to process something like that? And you know, if you know some kinds of behaviors of the system, how do you actually identify expressions that would be most likely to fit better?
Well, there are several things that you can try. I mean, besides having a general understanding of the system and seeing if the terms make sense or not, you can also try plugging that back in. So symbolic regression.gl actually has an interface for going from dynamic expressions, which is the symbolic backend that it uses, to symbolics.gl, so that you can then utilize those expressions in the original MTK model and then see how that goes. And you can then see if, like, you can do predictions, like you just use the first half of your data or something like that and then evaluate how do you do on the rest.
Okay, I think that's all the time we have. Let's thank the speaker again, and the next speaker can prepare himself.
Yeah. Just to make sure that I'm not...
I didn't read the I'm just filling in.
Yeah, no, thank you. Is that gonna go full screen for me? Oh, that's not gonna do it.
Yeah, in our next talk, Jack will be talking about applying SciML to ecological systems.
Yeah, right on.
Thank you so much. All right. Yeah, well, thanks for those of you who are here. I appreciate having some audience. The goal of this talk is I'm an ecologist by background and training, so me and my group have been getting really interested in trying to think about some of these tools that have been developed more in the machine learning and computer science worlds can be applied into our realm. And so rather than doing a lot of really technical details, I'm mostly going to be talking about how we're thinking about these problems with the goal of maybe having some sort of transfer learning back, because there are some features of the data sets and problems we've been working on that have required some modifications of these tools. So I'm sort of reporting in from a larger group of primarily ecologists that have been working on this in a working group. And so mostly going to be talking about work that I've led, but also there's stuff from this wide group of co-authors. And yeah, Chris isn't here, but he was actually pretty helpful at the very early stages of sort of conceptualizing some of the big picture ideas in this project. And yeah, we have like two big picture goals that the group's been thinking about. One is trying to explore how these sort of new scientific machine learning tools can be applied in our discipline, and to sort of modify and tailor them to deal with some of the specific issues that we face. And then we're also trying to write software to make these more accessible to people in our field. So this package, Universal Diffie-Q, is in Julia. It's trying to have a relatively simple to use front end on top of some of the sort of SciML ecosystem. And then we're also trying to export functions from that into the R programming language, which is a lot more common, which is a lot more commonly used. So the idea is get some of the functionality out of Julia into something where people are already doing a lot of their data processing and management. So the big picture question that's motivating all this work is a relatively simple one, which is we want to understand how ecological systems are changing over time. So that could be things like the coral reef and sort of savanna that I've shown here. And this is I think, important question to be thinking about for a number of reasons. One is if we can understand these sort of patterns of ecological change, particularly in the face of climate change, we can do things like identify more effective strategies for conserving biodiversity or managing natural resources. We can help people that are dependent on natural resources plan and adapt to changing environments. And there's also lots of fun and interesting basic science questions that can be helped out significantly by understanding how ecosystems are changing over time, such as what factors are contributing to the distribution and abundance of different species, as well as some basic science questions about evolution. However, this is a fairly complex problem or difficult problem to understand and solve because ecological systems often exhibit really complex dynamics. And to sort of formally define what complex dynamics are, it's essentially when simple interactions between ecosystem components produce complex emergent behaviors at the sort of population or system level. So a sort of canonical example of this would be relatively simple trophic interactions, like a predator-prey interaction between species can produce sort of cycling population dynamics over time. And these patterns of change can become more complicated, so theoretical models can show that if you add an additional species into that analysis and you have a food chain rather than that sort of mutual pair, you can get unpredictable sort of chaotic dynamics. And there are other patterns that are quite important as well. So for example, a lot of species will modify their environment sort of locally in ways that support their own persistence. And this can create positive feedback loops that result in sort of nonlinear shifts in ecosystem states over time. So how do we understand and predict the behavior of these sort of complex dynamical systems? One option is to try to predict patterns directly from processes. So this would be having an understanding of what's going on in the biology and then using mathematical models to pick up on what those sort of high-level emergent properties may be. And then the other approach is to try to infer processes directly from patterns. So we have a time series and we fit a model to it. There's some serious limitations, though, with these approaches. So one issue with this predicting patterns from processes is that small errors in mechanisms can lead to really large errors in predictions, particularly when there's sort of strong nonlinear sort of feedbacks involved. Another thing that can happen is that sort of patterns can be, oftentimes patterns will be able to be explained by many different possible mechanisms. And in particular in ecological systems, which is where I focus at, the dynamics of the system are quite slow. So we can't just run an experiment hundreds of times. If we want to understand patterns of change over half a century, it's going to take 50 years to get the data set. And so we have to be able to deal with these sort of essentially fairly limited information available just from this sort of time series data perspective. And so the goal, I think, behind the work our group has been doing is trying to sort of synthesize these multiple ways we can learn about ecosystems. So we have sort of observational type studies of those sort of high-level patterns that we can try to train models on, and we also have mechanistic information from biologists doing sort of field experiments. And we think these scientific machine learning tools can be a way of synthesizing these two sources of information to get a better understanding of the systems that we study. And there's a lot of different scientific machine learning tools that we think can be used to potentially get at this. So things like physics-informed neural networks do this by incorporating sort of mechanistic information into the loss function when you're training the models. There's also methods called knowledge-guided machine learning, which will train models on output from simulated data, from mechanistic models, from simulated data to incorporate mechanisms, and then train them on empirical data. And then the methods that we've been really focusing on are universal differential equations. And the idea is here we just build mechanisms directly into the model structure. Yeah, and so yeah, this is the main thing that we've been focusing on. I have a brief overview on this. I mean, I'm sure you guys know well what's going on here. But the basic idea is a universal differential equation is some differential equation describing a change in a state variable x. And it's got a neural network embedded somewhere on the right-hand side. It's often an additive relationship, but it could be something more arbitrary. And that the nature of this function is going to encode sort of mechanistic information and physical constraints. And the neural network term can learn sort of unknown components of the system or sort of unknown functions in that are sort of embedded in that system's dynamics. A sort of great example, this would be sort of a local Volterra model. So this is describing that sort of predator-prey interaction I was describing at the beginning. There's a term for the growth of the prey population, orange term that describes the predation, and then a sort of mortality rate term as well. And as an example, you could replace, if you didn't know or you thought there was a more complicated relationship going on in this sort of predation term, that could be replaced with a neural network. So based on that, we had a few different research questions that we've been exploring. So one question that we've been thinking about is trying to understand what the best methods for training universal differential equations are, given the sort of the challenges and limitations of the time series data that we have available to us in our field. We also want to understand, so ecological systems can exhibit lots of different types of complex emergent phenomenon. So they're, at least particularly in a time series context, there are systems that will exhibit sort of oscillating dynamics, sort of unpredictable chaotic dynamics, as well as sort of nonlinear responses to external factors called regime shifts. And so we want to understand when are these methods going to help us across these different types of dynamics that we might be interested in studying. And then we also want to understand, like, does it actually help to incorporate biological mechanisms, or should we just be training really flexible models like a node instead of a UDE? So to kind of go after that first question, one of the big issues we had when we started trying to work with these methods is that time series data in ecology tend to be quite noisy. And as I said before, they tend to be relatively limited. So we don't have a nice sort of engineering physical system that we can, put oscilloscopes on in different places and really figure out what's going on. So we often have data sets that have strong patterns of nonlinear change. So for example, a regime shift, which is occurring in the middle of this time series, driven by sort of biological feedback mechanisms. But we also see a lot of variability driven by sort of external factors that we don't necessarily observe perfectly. So there's lots of variability at the beginning of this time series that's well known to be caused by certain sort of variability in climate. And sometimes things are just hard to observe. So we also have sort of variability that's just due to noise in the observation process. And so one of the things that we've done is working on being able to deal with these sources of observation and measurement error when training universal differential equations. And so something we've done to make them more robust to these forms of uncertainty is embed them within a state space modeling formulation. And I'm not going to go into huge details about how that's done mathematically, but essentially what we try to do is, while we're training the model in the loss function, we use a probabilistic model that accounts for those sources of uncertainty. And as a sort of a benchmark, we've done a couple comparisons with other alternative methods for training UDE models. So one that I'm calling sort of a shooting method, where you just simulate trajectories of the ODE and you compare that to the data. And a gradient matching approach, where you fit a smoothing curve to the data, and then you train the model by matching the derivatives of the smoothing curve to the derivatives of the ODE model. And we've done some more extensive benchmarking than this, but these are the ones I'm going to present results for. And yeah, so one of the reasons we're interested in this is because sometimes we'll get data sets that look like this. So this is a data set simulated from a 3-species sort of food web model that exhibits chaotic dynamics with just a little bit of observational noise and sort of process noise added in, so a little bit of stochasticity. And what we end up getting are these highly variable time series data sets that are quite challenging for like smooth fitting functions and just simulating trajectories of the differential equations. And so we trained a bunch of models on different simulated data sets, simulating the random numbers differently to figure out the sampling error. And we trained these sort of UDE models with the 3 different approaches. We have sort of 2 different formulations for the state space modeling framework. And then we have the sort of gradient matching and shooting methods. And then the 4 different panels just show different levels of sort of noise added into the data set. And the x-axis is different forecasting horizons. And this was repeated hundreds of times on different simulated data sets. And we found that very consistently having this more explicit mathematical representation of the uncertainty made the model training process a lot more robust to the common types of uncertainty in our field, at least for this system. We also ran these on a different time series. It had, so instead of that sort of highly variable, almost oscillating type dynamics, we looked at a system that had periodic regime shifts. So there are strong nonlinear dynamics internal to the system that can cause it to flicker between alternative stable states. And that's driven by some variable abiotic conditions. And again, we use sort of a forecast, we use simulation tests to look at the forecasting skill of the same universal differential equations trained with different methods. And in this case, this sort of gradient matching approach was the most effective, but the state space models were, in some cases, within the margin of error on our simulation analysis, so performing quite similarly. So this was like sort of one of the big first challenges. Like, this is allowing us to actually test these models and use them on sort of empirical data sets for environmental systems. And to answer my sort of motivating question here, what's the best method for training these models? It seems like it's a bit problem dependent. The state space model formulation is probably the most robust to uncertainty, but it adds quite a bit of computational cost. And since I'm not primarily a computer programmer, our code could probably be written a little more efficiently. And sort of gradient matching technique is probably the lowest computational cost because you avoid all the ODE solvers entirely in the sort of training process, which helps quite a bit. And the shooting method can be really nice in some cases because it restricts the solutions sort of predicted by the model to solutions of a differential equation, which kind of adds some regularization. But in general, with these highly uncertain data sets, embedding UDEs within a state space model helped a lot. Yeah, and within our sort of modeling, within this sort of software package we've been putting together, we have a relatively simple interface to access all these different methods, this train function. Oops. The next big set of questions and problems we looked at was trying to understand how well universal differential equations could identify and forecast regime changes in particular from time series data in ecology. And regime changes are essentially when small changes in external factors in the environment lead to large and persistent changes in the structure, so the types of species that are around, and the function, the types of ecosystem services that are produced by an ecosystem. And some examples of that include in like tropical nearshore ecosystems, reefs can be dominated either by corals or sort of macroalgae, and that depends a bit on temperature and also sort of biological feedbacks that maintain either alternative state. A similar process can happen in arid environments where they can often be either dominated by sort of grass species or a more desertified shrubland dominated state. And this is quite important because these regime shifts can be accompanied by major changes in ecosystem services, such as like carbon storage, water quality, or like soil erosion. And there can also be losses of economic value from things like grazing, fisheries, and sort of other use, ecotourism, and other uses of these ecosystems. So to think about this question, we started looking at, rather than those simulated data sets, some empirical data sets. And one of the first ones we looked at was this sort of long-term monitoring data set. I keep kind of flashing up on my different slides, documenting the abundances of perennial grasses versus sort of shrub species in an experimental rangeland in New Mexico. And this sort of exhibits this regime change from a sort of grassland-dominated to a shrub-dominated state in around the year 1950. And this was caused by a sort of major period of drought that occurred during that time. So there's significant declines in precipitation and increases in pressure that actually had to do with conditions in the Pacific Ocean. And that caused this long and, importantly, persistent shift, even though the sort of abiotic conditions or physical conditions of the system returned to their states before the regime shift occurred, the biology didn't. And one of the reasons people think that we had this sort of shock in terms of the physics of the system influencing the biology in a persistent way is that sort of grasses in these arid rangelands can modify the conditions to improve their level of persistence. So when there's lots of grasses around, essentially rainfall is much more likely to infiltrate into the soil, so increasing soil moisture levels. Whereas when they're less persistent, it'll run off and erode, reducing soil moisture levels. And so if they go away, they can't necessarily come back. So we developed two universal differential equation models, one that tried to explicitly incorporate this feedback mechanism between plants and soil conditions, and another one that only included sort of physical constraints on the system. So essentially the data set tracks the percentage of space covered by different species, so we imposed a constraint that everything had to add up to 1. And so we trained these two different models on those data sets using the state space modeling approach. And the next thing we did was we used those trained models to generate bifurcation diagrams. And so what these do is they track a variable, so in this case precipitation, along the x-axis, and along the y-axis is the equilibrium density of a species predicted by the model. So you set the right-hand side of the differential equation to 0, and you solve using a nonlinear solver. And the different panels show the different species that we used in these models, and then the different rows show the two different UDE models that we tested. And we found that they both were able to recover this potential for regime shifts in the system with a high abundance equilibrium of grasses and a low abundance equilibrium. And very qualitatively similar bifurcation diagrams for the grass species, and then fairly different looking ones for the other species included in the system. So it seems like these methods are able to recover this potentially quite important form of nonlinear dynamics from time series data. The other thing we wanted to know is if you could figure out if regime shifts were going to occur before the sort of tipping point actually was crossed. So this tipping point's crossed around 1950, where you get this transition from a grassland-dominated state to a desert-type state. And we just constructed some data sets by leaving off the end of the data there. And we trained the model sort of moving up along each of these data sets. So that's starting at the top of this figure, moving down to the bottom, and looked to see what kinds of bifurcation diagrams were predicted, where the sort of tipping point between these two alternative stable states was. And what we found was that the model with more sort of mechanistic information and structure in it, UD2, predicted where the sort of tipping point between these two regimes was much more consistently than the one that only included the physical constraints. Yeah, this jumped to this. Okay. The other thing that we did was we ran just leave future out cross-validation to see how well these two different models forecasted. And we did this twice. We did one set of training sets just based on the end of the time series. And then we did another one where the training sets were mostly constructed or the testing sets were mostly constructed around that regime shift. And we found, we compared the two universal differential equation models to basically a linear time series model. And the UDs, the more flexible universal differential equation model that didn't include all the mechanisms was the most effective at making forecasts. So in terms of our big picture questions, what we found was that sort of universal differential equations can be quite nice for predicting regime changes from ecosystem time series data. It seemed like including additional mechanistic information in the model improved the model's ability to detect where tipping points were in the data set. But more flexible UDs that are primarily learned from data seem to be better at forecasting. So there's a bit of a trade-off there. We also have other people in our group trying to think about this sort of coral reef macroalgae transition that's sort of really determined by sort of fish populations. But they've been a lot more ambitious, and they're looking at sort of global data sets of the global scope, and they're looking at a lot of additional drivers that are really important for coral reefs. So this is still sort of in the works. Another sort of piece of future work that I'm really excited about that'd be cool to get people's feedback on is thinking about how to scale these models up to really, really large data sets. So we have a lot of satellite-based remote sensing data is often highly relevant, and that can lead to data sets with potentially, this is like a 30-meter resolution data set that's global, so millions of data points. We're also interested in understanding harmful algal blooms in lakes. And again, these sort of satellite-based data sets are great for that. Yeah, finally, we're working on essentially trying to get a front end going for these tools to allow other people in our field to use them efficiently. Lots of people in ecology already use, like R is kind of the main thing that people use for making figures and analyzing data sets. So we want to get these functions basically from our Julia package to be accessible there. So we're using the R to Julia to do that. And yeah, we want to make sure we're generating sort of new methods for training these models that are sort of, that deal with a lot of the realities and limitations of the data that we have to work with. And yeah, with that, I'll wrap up a bit early. But
any questions for the speaker? Yes. Hi. Thank you for the talk. I have a question. You mentioned some training techniques with gradient matching. In that case, when you're estimating the gradients from data, what do you use to avoid noisy gradients? So I assume that you mentioned that your data is very noisy, so I assume that if you were to try to do gradients naively from that, it would be impossible to use because you would have very much.
Yeah, so you end up having to fit sort of smoothing functions that have some form of regularization. So I have one implementation going that uses interpolations JL to do some of the like nonlinear or this like smooth curve fitting type approach. So there's a penalty term on the derivative to keep it from, so you get a nice smooth curve rather than, something that just runs through each of those data points and gives you a very noisy gradient. Another thing that you can do is you can estimate that smoothing curve and then you can penalize it to have to match the derivatives predicted by the model. I'm not sure. So you simultaneously train the neural network and fit the smoothing curve to the data, and you add a penalty term so that the derivatives of the UD model have to match the derivatives in the smoothing curve, and that'll simultaneously train the UD model to match the data, and it will regularize the smoothing curve. And that method seems to work the best. It runs really fast, and it deals with some of the noise issues. So that's something we're still kind of working on, figuring out the best way to implement it. I've seen some things where you'll use a neural network to learn this basically smoothing function, and then another one to learn the derivatives. We've been finding just like basically like B-splines, so like polynomial spline works pretty well too.
Okay, are there any other questions for the speaker? I have a question. Since your systems are inherently much more uncertain, more variable than the typical engineering applications that we often see in these SciML talks, do you think it would be useful to also apply these methods to like stochastic differential equations or these jump problems that are also present in the SciML ecosystem?
Yeah, I think something we should probably be working on is particularly like the jump problems. So there's a lot of models, a lot of theoretical models in ecology will use something called like a pulse-impulsive model or a jump differential equation to account for like seasonality, because a lot of species in the life history will have like a pulse event where they release a bunch of like propagules into the environment or something along those lines. We've thought about trying to implement this stuff with stochastic differential equations as well. And the sort of state space method we've worked on, I think, is a good sort of pragmatic in between where you don't necessarily have to simulate lots of individual trajectories. The other thing is that sort of smoothing curve method I was telling you about if you pick the order of your B-spline correctly, it ends up actually being approximate inference for stochastic differential equations, depending on how you set up the algorithm. And you don't have to ever deal with an ODE solver. You just match derivatives of a smoothing function and the UDE model. So that's kind of one way of approaching it.
Okay. Any other questions for the speaker? Otherwise, let's give another round of applause, and then the next speaker can prepare.
Yay. Okay. There you go. Yeah, we'll wait, I think 5 minutes.
So at the same time, training the neural network inside.
But chronologically, we need to wait for 3.5 more minutes. Thank you.
Let me see if my tutorial is fine. I think so. Sounds good. Seems fine.
Your name is pronounced Leticia?
Leticia, yes.
I will give you a quick introduction.
Okay, thank you so much.
Normally Chris is supposed to be doing this, but he's in another session. Okay, our next speaker is Leticia, and I'm excited to learn about SciML in quantum chemistry.
Thank you so much. So I'll be talking about optimization of Gaussian basis sets with automatic differentiation. I am Leticia. I'm a PhD student at Carnegie Mellon, working in the Department of Chemistry. And here, just an overview of my GitHub profile. I have an organization called Hartree-Fokker, which is a computational chemistry-based organization with packages and software that relies on neural networks and Mackey-Davidson formalism. My research areas are catalysis, polymerization, quantum chemistry, electron-electron correlation, and chemical bonding. I'm not an optimization person, but I'm happy to be in this session and talk more about it and how I'm using it on my work here. This is also independent work, not exactly my thesis track work. And I'm also happy to take people that want to contribute to my packages. Okay. So an outline of the presentation, I will start introducing the electronic problem in quantum chemistry. So this is a quantum chemistry 101 slide. I'll explain the formation of a chemical bond, the nature of the Gaussian theorem and how it applies to the study of wave functions. Why do we use Gaussians to approximate wave functions and atomic orbitals? And then I'll give a shout out to Sir John Popo, and then I'll explain when we get there. Also, I will show the basis set exchange, which is the database that I use, and then I will introduce my package and some of the features that I implemented. We'll have a demo if everything works out, and I will show how do we run an electronic structure calculation using a basis set that we'll design today live, and some of the future work that I plan to do, and some of my hackathon plans for tomorrow. Okay, so for those of you who are not familiar with quantum chemistry, the whole goal is to solve the Schrödinger's equation and calculate the total energy of the system based on how many electrons and what are the interactions present in it. So consider this system here. You have two atomic nucleus and you have two electrons. So pretend this is a hydrogen molecule, and you need to calculate the energy based on all the interactions. So the repulsion between the nucleus, the attraction between electrons and nucleus, and also the repulsion between electrons. And as the system grows in size and number of electrons, it becomes harder and harder to compute those interactions. So you need to rely on approximations, right? And one of the things that we also search for in quantum chemistry problems is the wave function, which is our oracle and gives you all the information about the system that you are studying. How do we approximate this wave function, which is this psi that appears on our Schrödinger's equation here? And we expand it in terms of the molecular orbitals. And we write it as what we call a Slater determinant, which is an antisymmetric determinant for the particles in the system. And each molecular orbital is expanded as a linear combination of atomic orbital functions. So you can see the third equation here. And C's are the contribution coefficients in the linear combination, and K's are the atomic orbitals, right? But what is the mathematical shape of the atomic orbitals? That's what we are going to discuss. So if you understand the slide, you understand quantum chemistry. Woohoo. And you can start calling yourself a quantum chemist. Looking at the chemical bond from an electron density perspective, for some of you that were in my talk in the morning, you saw a similar slide today, so it's real. I'm reusing the same slide from the morning in this case. So hydrogen, the hydrogen molecule, you have one s orbital in one hydrogen, the one s orbital in the other hydrogen. You have a linear combination of those, and then you form bonding and anti-bonding orbitals. The bonding orbital is a positive combination, and the anti-bonding orbital is a negative combination. That's why you have this nodal plan, and you have the different colors in each one of the lobes in what we call molecular orbital. And why this is important? In this case, we have a homonuclear diatomic molecule, so both atoms are the same. So 50%, we have 50% of contribution from one hydrogen, 50% from the other hydrogen. But when you have larger systems or different atoms participating in the bond, these contributions can be really tricky to find. So we need to optimize and find what are the contributions for the different atomic orbitals in the formation of the molecular orbitals. So, okay, now that we introduced atomic molecular orbitals and the Schrödinger's equation, what is the mathematical form of an atomic orbital? In reality, if you solve analytically the Schrödinger's equation for the hydrogen atom, you'll get what we call a Slater type function or Slater type orbital, which mathematically is represented by a Lorentzian distribution. So you have the plot on the top. So consider each color one different hydrogen here. So you have STO from atom A, STO from atom B, and STO stands for a Slater type orbital. If you calculate the overlap between the two functions, which is this intermediate region, which will determine how much bonding there is between the two atoms, you'll see that your overlap integral is very hard to obtain because the function will be discontinuous. You have this cusp there, which makes computation of this very hard. Think about having thousands of electrons in your system and trying to compute overlap and chemical bonds for all of them. If this function is discontinuous and you need to use a quadrature to solve the overlap integral for all of them, it will take forever. So it becomes not doable. So what we do in quantum chemistry, we use what we call Gaussian basis sets. Gaussians are much easier to compute, and because of the Gaussian product theorem, if you compute the overlap between two Gaussians, you obtain a Gaussian. So it makes our lives much easier. So just a recap, why do we use it? Why do we use Gaussians in quantum chemistry? First, because you can analytically solve the integrals, the overlap integrals for these, in comparison to Slater type orbitals, which require the use of a numerical quadrature or expansion to be resolved. Each new property, if you're using Slater type orbitals, require a new numerical solver setup. And in comparison to Gaussian type orbitals, which adding more and more and more functions does not incur into much more cost of computation. And I have a demonstration because I'm telling you, oh, it costs less to use Gaussians, but how much less, right? I would like to show you the numbers. So I will just demo real quickly. Oh, I messed up my own password. Okay, again. Cool. So benchmarking is our first part of this demonstration. I'm using Quad GK and benchmark tools. Gaussian overlap, I just put the solution here. This is the analytical solution for an overlap integral between two Gaussians. Here I have Slater overlap, and then I'm using a quadrature. I'm not really worrying about that much accuracy or details on this computation. I just really want to show how dramatic the difference is, right? And then here parameters for my Gaussians and my Slater functions. Just single shot results, one Gaussian overlap, one Slater overlap. And the timings are here. And the numbers don't lie. You can see how much faster it is to use Gaussian basis sets. to compute molecular integrals and solve the Schrödinger equation, right? Okay, so we have the results. And this justifies why we are using Gaussians. And we are in Pittsburgh. And what does Pittsburgh have to do with Gaussians? So in the chemistry department, we had a professor called Sir John Popple. He won the Nobel Prize in Chemistry in 1998, and he was a CMU professor. And he actually was the first one to apply this approach of using Gaussian type functions to approximate atomic orbitals and compute molecular integrals. So you can see here that what he proposed, and this is one of his most cited papers, which show the use of Gaussians. He proposed that by adding more and more Gaussians, you would approximate better the cusp of your Slater type function. So your Slater type function would be your reference, and then you add and you do a linear combination of Gaussians to approximate this atomic orbital. And here, for pedagogical purposes, I'm going to use basis sets and atomic orbitals interchangeably, but they are not necessarily equivalent. But I'm not going into much detail there. And he developed a software, which is one of the most used softwares in computational chemistry, called Gaussian. So here is the paper where he shows this, and citations. So since 2016, this paper was downloaded 4,000 times, and it has almost 9,000 citations. And his Nobel Prize medal is located in Hunt's library at CMU, and you can visit and take a picture with his Nobel Prize medal. So just wanted to show this because it's also a Pittsburgh thing. It has a relationship to this place and to Carnegie Mellon. Okay, so John Popple proved that this worked. He showed this approach, and he designed basis sets combining Gaussians. And people started using and developing basis sets on and on and on, with different Gaussian shapes, with different philosophies, adding polarization functions, using different fragmentation schemes to compute all sorts of properties and interactions, right? And we have a collection of these papers. And how can I access all the basis sets available in literature? There is this database called Basis Set Exchange. Basis Set Exchange is hosted online. So it has nearly 750 basis sets. You can click on the basis set you want to use, and it shows, oh, it's available for such and such atoms. And then you define which format you want to download your basis set, and that's it. And that's what computational chemistry softwares use to run calculations. So this is an example of the format of a basis set. Again, hydrogen, simplest example, STO3G basis set. So this means that I'm using 3 Gaussians to approximate 1 Slater type orbital. And then you have here highlighted the column which shows the exponent factors of the Gaussians, and the column which shows the contraction coefficients of the Gaussian, and this is the mathematical expansion of this. So this is the expression, this is your basis set for 1s orbital in hydrogen, and this is a general form of this basis set. So these are your contraction coefficients, and alphas are your exponent factors. And how did they obtain this? They optimized these coefficients and found, using least squares, the coefficients that would optimize this basis set for hydrogen. Okay, and they also have an API, and they structure their API this way. So you have layers of JSON files, one with the basis set. The second layer will contain the element, so the element of the periodic table, and the third layer will contain the components of that basis set. So you have every time you want to get one basis set, you need to process at least 3 different files, which is annoying. So what I did, I developed this package called basisset.jl, which works as a wrapper for basis set exchange, first of all. And it's going to parse all of this for you and return a structure which is compatible with all atoms-based and Julia molecular simulations environments. So if you're not familiar with Julia MolSim, there is a mini happening over here for material science and computational chemistry, and people are talking about the packages in this organization. So it returns a Gaussian basis set structure with all the data, coefficients, coordinates, everything we need to know about that basis set. And it's compatible with that environment as well. But basisset.jl does not only form new data structures for existing basis sets, but it currently supports optimization of brand new basis sets, and that's what I want to talk about. And this is where I use automatic differentiation. So the problem is, given a k number of Gaussians, can we minimize contraction coefficients, so D's, and exponents, alphas? Can we find what are the best coefficients for a given basis set setup? And it turns out that we can. The ideal scenario would be if you have an infinite number of Gaussians, but you can't. So you need to limit yourself and do some approximations, right? So the idea is you have 2 stages of optimization. You have an inner stage, which is cheap, and you use least squares, and this is going to give you the best contraction coefficients. And then you have the outer stage, which is the most expensive one. And then you need to calculate the integrals utilizing your D coefficients that you just found. And you need to run a self-consistent field cycle, which will basically optimize your exponents. And then you backpropagate to the elements of this exponent, depending on which mathematical expression you define for it. And you find the coefficients which have the lowest, which give you, at the end, the lowest root mean squared error. And then you define the threshold. So here I'm showing the first part, which shows the optimization. You define the problem objective function, the boundary conditions. You define the algorithm that you are using. In this case, just to simplify the example, just LB FGS. And I'm minimizing to find the alphas and the coefficients. And here, just to finalize, I'm showing how my least squares algorithm is set up, and I want to demonstrate how this works. So I'm going to VS Code, and I'm going to show one example. Okay. So part 2, I'll use 2 of my packages, basis sets and Ohata Uzinaga, which basically runs the STF cycle for you. So molecule that I'm using, hydrogen, because this is a tutorial, so I needed to choose something that would be small enough that we could run live. And I'm going to actually run it so you can see how fast it is. Here I'm defining the shell table, which is basically the shape of the basis set that I want. So I want 1s orbital for hydrogen, and I want 3 Gaussians. If I want more functions, I can just keep adding to this list. So I defined the shell table. I have the function optimize basis. So it's going to run. It ran. It optimized the basis for the first hydrogen atom. It optimized the basis for the second hydrogen atom. It returned the Gaussian basis set object from each structure. You can see how this is organized. If you look at the basis set for the first hydrogen, you have coordinates, you have these, you will have alphas, and then you will have the quantum numbers. So now I'm going to just calculate the energy and see how good this energy is. So I'm using my Ohata-Huzinaga package, restricted Hartree-Fock calculation, and I define the basis set, my molecule, overlap integrals are done, kinetic integrals are done, attraction integrals are done, repulsion. My Hamiltonian is calculated, my SCF iterations are running, and I get the energy here. The exact energy would be closer to -2, so this is actually pretty good. And the unit is Hartree, which is what we call atomic units. So this basis set actually works and gives you a reasonable energy at the end, which makes me quite happy. We just ran a calculation with a basis set that we just developed. So that's quite exciting. Why this approach is especially useful? We just saw that it allows for very fast prototyping, immediate usability of brand new designed basis sets. It helps you with method development in general for quantum chemistry. So you can set up whatever shape you want for your Gaussian functions for your basis sets, and you can account for interactions that are specific to your molecular system. And this is a good and a bad thing, because this means that as of now, my implementation supports a local scope application, which means that that basis set is applied to that molecular system specifically, which can be good if you are working with very specific challenges. But I want to expand and make the basis set available for all other systems. So for example, hydrogen in all molecules, or hydrogen in a given set of molecules. So make my basis sets support a broader scope of molecular systems. For future work, so as a wrapper, I want this package to export the basis set that the user creates in a format that basis set exchange supports. And I also want to write a GitHub Actions protocol that automatically updates the repository and can submit the pull request as basis sets are created. Detail, I need to implement, for this to work, one, of course, the pull request would be submitted by the request of the user if they want their basis set to be available in basis set exchange. I need to write several tests that would verify the quality of that basis set and see if it is a reasonable basis set based on reference functions that I have. And once it passes all tests, then I could submit as a pull request. So I want direct communication with basis set exchange, which is basically the reference for all quantum chemistry calculations in terms of where you get your basis sets. Next step, I need to update the documentation of this package, showing how to use these new functionalities. And these are things that I plan to do at the hackathon tomorrow. So if you want to join me, if you want to discuss more things about this package, you're welcome to do so. I will be around. And from a scientific perspective, what I want to do, I also want to add effective core potential corrections for relativistic effects. So when you are looking at heavier atoms in the periodic table, you need to account for relativistic effects. By heavier atoms, I mean like gold, silver. These atoms really require relativistic corrections for energies to be reasonable and accurate. So I need to add Gaussians that would support effective core potential corrections. And also develop an automated engine that would recommend basis sets based on your molecular system. This is not something available out there, so there is no implementation of something like this. So I want to do that, and I want this package to be a whole factory for Gaussian basis sets. And I will take advantage, and for this, I will be taking advantage of packages like forward diff and the whole SciML ecosystem, which allows and provides very good alternatives and packages for optimization and differential equation solvers and all of that. So on that note, I would like to thank everybody for your attention. Here's a QR code for my GitHub, and I would like to thank the chemistry department at CMU, my advisor, committee members, NSF, PSC, the Pittsburgh Supercomputing Center, and I'm open for questions if you have any questions, suggestions, comments.
Questions for the speaker?
Thank you for the talk. I was wondering, do you think it would help if you were to use a symbolic approach for when you're doing the optimization step codes? There are, I mean, you could represent that symbolically and maybe take like symbolic derivatives, or?
Yes, I 100% think so. And I wanted to implement this by JuliaCon, but didn't happen for PhD reasons. But definitely, that's the next thing I want to test, because I still think my approach could be more efficient, and I think it's a perfect case suitable for symbolic optimization. So yeah, definitely. And if you want to chat about it at the hackathon, I'll be around.
Yep, more questions?
Thank you for the talk. This is great work. And I have two questions. And the calculation of the STO type, yeah, basis functions, we minimize the not energy, the overlap integral to the exact solution.
Yes. Yes, you minimize the error between the STO reference, so your Slater type orbital function, and your Gaussian expansion.
Yes.
So that's the error that you want to minimize.
In your new plan, what is the objective function to minimize energy or overlap?
No, it's the Slater type function. Okay. So yeah, so I want to minimize with respect to that reference.
I see.
Not the energy. And the energy I obtain at the end.
Okay, and I have one more question. And about the struct of the basis function data, you set the type float to 64.
Yes.
Is there some reason to restrict double precision?
I could do that. I haven't played too much with the precision. Maybe it's something that I can do. I don't know if we need like more precision than float 64.
I see.
But yeah, it's something that to play with. Yeah, and for the structure of the basis set, so this example, I know that you'll know what I'm talking about. This is an even-tempered basis set. So that's why I'm defining my alphas in terms of betas and gammas, but that's it.
Okay, one more quick question while the next speaker sets up.
Would you speak for a moment about the propagation of error in how the error in your approximation with the Gaussian basis propagates to energy and other downstream computations?
So there is something that we call basis set superposition error. And this is something that happens when you have a basis set that is imbalanced with the size of your atom. So that's one big problem when you are designing basis sets, which means that you will overestimate the energy and you overestimate the interactions because you have bigger basis sets than your atomic sizes, basically, roughly saying. So this is something to account for, and it's not currently implemented here. So what I could do, I could just write a function that estimates this basis set superposition error. It's a little bit expensive, so that's why I didn't do it yet. And then I can just correct the energy at the end with this basis set superposition error that I estimate. But it does, yeah, there is a lot of propagation, and it increases when you have a bigger system because they propagate for each and every interaction, each and every bond in your molecule. So you need to be careful with that.
Thank you.
Thank you.
You can have the pointer if you want. Yes. Those. Yeah. Yeah. For me. Okay, yeah, so I'm the next speaker, held by Sebastian. I'm Arno, I'm a statistician focused on experimental design. We will be applying this to SciML in this talk, and Sebastian helped me with some of the trickier programming aspects. And Sebastian is gonna start by introducing some of the background SciML material that you need to know to be able to perform experimental design.
Hello. So, as we've seen in other talks, we have a lot of in the field of scientific machine learning, and as we know, this combines the idea of using our existing mechanistic scientific models with experimentally acquired data, and how we can best combine them to produce better results and to fill in missing gaps. In this particular case, we are looking at some missing parts in a larger known model, and we have examples such as these pictures where we have some reactions where you might not know everything, but you know a lot of the surrounding reactions and the surrounding terms are very well known, but there are some concrete missing parts in the model. And to showcase this better, we're going to start with a concrete case study on a bioreactor. So that's the bioreactor in question, and we already know quite a lot about bioreactors. So what does the system do? So we have three main differential equations, and physically what they represent, we have concentrations of substrate, which is CS, and then we have concentrations of biomass, because it's a bioreactor, so there are some tiny creatures in there that eat the substrate, which is the food, and of course the volume of this entire thing. So we can control the volume by pumping in more substrate, so that's more food for the biomass, so it will grow. So we know that, for example, by pumping in substrate, which is this Q in, we're going to increase the volume. We know that if you increase the concentration of the substrate, then you're going to have more biomass because they feed on that. You know that if you have too much, sorry, so let's go back. Yeah, when we pump more, so the term right there. Sorry, I have the mouse for a reason. So when we pump more substrate, we're going to decrease the concentration because it's going to get diluted. We know that if we have the biomass, sorry, is eating from the substrate, so that means that the more biomass we have, this is going to again decrease the concentration of substrate. And we know almost everything about the system, but as we've seen, there are certain parts here that we've symbolized with this neural network symbol. So this is the part that we're going to try to find out. So now, how are we going to do this? This is the moving to the experimental design part. So we want to design a series of experiments such that we can we can get these terms, and then after that, as we've seen with neural networks, we can interpret their results with symbolic regression. And we're going to use again the symbolic regression.jl package, which will help us understand the output of a neural network in terms of a symbolic expression. And now moving on to the experimental design part, as I was saying, we are gathering data by pumping that concentration. So we are going to start first an experiment where we have a low substrate concentration. And we're going to see how does the reactor behave in this case. And what we can measure in here are these blue dots. So this is our experimental data that we're going to use in this case. And then after we perform the experiment, we have our model with the neural network inside. We train the neural network. Then after we have this neural network trained, that's the orange line, then we will perform symbolic regression to understand what does this neural network look like in terms of a symbolic expression, so that we can understand the behavior of the system better. And we're going to repeat this process several times. And as you can see here, we have more candidates for symbolic regression. So these dashed lines are candidate models that were discovered with this process. So first train the neural network, then do symbolic regression during the result. We get several candidates, and each candidate is going to be a dashed line in these plots. And if you're wondering what's the blue line is the correct model. This is what we would expect to get. So this is the correct model. And as we can see, we get pretty good fits with the data. When we actually look at the missing physics component that we're interested in, we see that we are not that close outside of the region of small substrate concentrations, which is where we have gathered data for. And this makes sense. The neural network is not able to extrapolate past the regime where we collected data for and where it was trained. And what happens is that when we look at the possible candidates of component models that are predicted via symbolic regression, we see that we have two groups of two categories of models, essentially. We have a category of models that says, okay, the substrate concentration will, so this mu will continue to increase as the substrate concentration increases. And another category of potential models which says that it's going to remain low with an increase in the substrate rate concentration. So this is the growth rate that we have. And the true growth rate is this one, which is given by monokinetics. And this is what we are trying to see if we can recover by experimental design techniques. And here the important part that I want you to remember from this slide is that we have these two groups of candidate models. One says that this should increase, one says it should remain the same. And now I'm going to pass to Arno.
Okay, thank you, Sebastian. So the experimental design criterion that we used for designing our second experiment is written down here, but I can explain it in very simple terms. So we have these 10 plausible model structures produced by symbolic regression, and they give us different predictions. And then we will be performing the second experiments under those conditions where these predictions are as different as possible from one another, because once we then gather the data, at least some of these predictions will be incorrect. They will be then removed from the top 10 structures of best possible model structures, and they will be replaced by other plausible model structures, and in this way you can come to a sequential experimental design technique. So when we apply this criterion to the second experiment, we see that an experiment where the maximum amount of substrate gets pumped into the reactor. So a lot of food is pumped into the reactor. And then, yeah, as Sebastian clearly explained, there were two groups present in the top 10 plausible model structures, and this experiment allows us to discriminate between these two groups. The two groups will give us very different predictions, and then once we perform the experiment, one of these two groups at least is going to be eliminated. We actually performed the second experiment here, and now we see here that because we are pumping a lot of food into the reactor, we see that the substrate concentration grows very quickly, and then once the biomass grows exponentially here, we can see here that at the end, finally the substrate concentration is starting to go down because there is so much biomass present in the reactor that it starts to get eaten. So now when we look at our missing physics panel here, what we see here is that now we have a group of observations at high substrate concentration from our second experiment, and we still have present a group of measurements at low substrate concentration from our first experiment. And we see here that the neural network that we fits well at low concentration and at high concentration, but at, let's say, the middle here, medium concentration range, there is still a large discrepancy between the neural network and the true missing physics. And the same story goes for the 10 best possible model structures that symbolic regression can come up with. All of them fit well at high concentration and at low substrate concentration, but there is substantial uncertainty at the medium concentration range, which is to be expected because we don't have any experimental data in that regime yet, which then leads me to our third experiment. And this figure here is what really convinced me that there was something to this method, because a very clever experimental design was chosen here. I said that there was a lot of uncertainty at the medium concentration range, and what we see here is that first a small amount of substrate gets pumped into the reactor, which causes the substrate concentration to increase to this medium concentration range. Because there is a lot of uncertainty here, a lot of uncertainty in the prediction by the plausible model structures, we see here that the predictions start to diverge from one another. Then as time goes on, the biomass is eating the substrate, is eating the food, so the amount of biomass increases and they start eating more and more substrate. So to keep the reactor at the medium concentration range, where there is substantial disagreement between the plausible model structures, we need to keep pumping in more and more substrate into the jar to keep feeding the more biomass that keeps growing in the reactor, which is why this staircase profile is optimal. So what we really see here is that this experiment automatically tries to reduce the amount of uncertainty that was present at this medium concentration range. So this is really a very clever experiment, completely designed or chosen by the computer. After gathering this third data set, we can see here that the true model structure is recovered by symbolic regression. It is kind of in a funny form because symbolic regression doesn't know that minus minus can be replaced by a plus sign, and it has two divisions here, and it also doesn't know that it can just replace that by a multiplication by Umax. So it is kind of in a funny form, but the true model structure is recovered here. So one step that still requires some human intuition is selecting the final model structure. So it still takes some human input to figure out that these model structures that come before here are underfitting the data, and that the model structures that come after are overfitting the data. So that part is still not completely automated, and there can be still some improvement in that aspect of the algorithm. So that was the optimal experimental design methodology. We did a comparison where we just pumped a random amount of food into the bioreactor, a random amount of substrate. We gathered a similar amount of data, and then you can see that symbolic regression is not able to find the true model structure at all. So you can clearly see the added value of going for an optimal experimental design strategy. And then, I will hand it back over to Sebastian to talk about the methodology that we used.
So the demo presented here and all of these examples are available in the SciML showcase documentation. So if you go to the latest release of the SciML docs, you can find this, and there's also a QR code for this. And the main things that were used here were, of course, modeling toolkit neural net, which had a talk earlier, and also the symbolic regression.jl package, which is a very nice ecosystem on its own. And the idea would be how to best combine all of these technologies across Julia ecosystems to deliver more interesting ways to discover missing physics and do optimal experimental design in the context of universal differential equations. Thank you. I think you'll have a microphone. Yeah.
So, great presentation. Question. Well, more of a comment, and I'm sure you know as well. It really feels like the fitting of the symbolic regression is very misleading, because the task at hand is you already have a data-driven model that fits your curve, and what you're keen on is really finding an expression that makes a statement of not just the training data, but where this thing operates outside of that regime, which matches your dynamics. So, I don't even know. Is there such an interface in symbolic regression that allows instead of the fitting criteria to just be the training data, to at least help someone looking at the list of equations that you put out there, in the case where you don't know the equations? I mean, in some of these cases, thankfully we knew the actual expression, so we could pick out from the list of what was presented, hey, this is the correct one. But in the case when you don't know that, it seems like the most fitting way of doing such a thing is having some kind of validation on some additional trajectories that weren't part of the system. Are you aware of anything in symbolic regression that actually accounts for that during its a criteria of, I mean, it has the criteria of complexity, but.
So in symbolic regression, you can also use custom loss functions, which you could use to potentially incorporate other things in there. You would have to work with the symbolic regression, like dynamic expression representation there. So there are several approaches here. You can also work at that level. You can try to, as you mentioned, have some data that you are going to use for predictions and evaluate. So not use the entire time spent for training, use a part of it. Or you can also try to get back the expressions from symbolic regression and plug them back into the original model and then see how that goes. So there are several approaches here, and maybe Arno wants to also add some more. So if you have any other comments.
Yeah, just to more broadly answer this question. This is kind of an issue all over experimental data. So when you have observational data, it's very simple to just split up your data set into a test and a trained data set. Because, well, if you just select a random subset, then they have the same statistical properties. But when you design an experiment and then you want to later on validate, then yeah, how do you pick what to validate on? Because you pick your own experimental conditions. So I think just in general, there is not one way to do this in the literature. Not even for very basic experiments like linear regression, and then of course definitely not for these more complicated scenarios like symbolic regression. So it's an issue all over the experimental design literature in contrast to observational data.
Yeah, thank you so much for an amazing talk. So something I was really curious about is I've used a bit of symbolic regression high energy physics, and something that we have run into is finding a good way to estimate the uncertainty in the choice of function. Not really, in the fitting parameters of that function, but since symbolic regression outputs multiple possible candidate functions for your data, how do you quantify exactly what might be a reasonable uncertainty band for that function? Have you guys thought about that at all?
Yeah, this was kind of what I was alluding to at the end, that it still requires a lot of human intuition to select the final model structure. There really isn't any way to do like some type of more rigorous inference to really get to like a confidence region or confidence set for the possible model structures that we are aware of. We are also not really researchers in symbolic regression. I'm more in experimental design, and Sebastian is more in computer science. So we are also not experts in that area. Maybe you can ask Miles, the creator of the symbolic regression package. He's going to probably be able to answer that better than we can.
Thanks. So something else that I was a little bit confused by was why in the study we're using both a neural net and symbolic regression. It seems like if you're just looking for something to predict your data, symbolic regression on its own might have been fine, no?
Yeah, we can use this new feature in symbolic regression for that, where they have like these templates now to do this. And indeed, that's the next thing we're planning on doing, on cutting out the neural network. And we have to finish that paper before November.
Yeah, just to comment about that as well. I feel like when you're trying to at least discover the missing physics and whatnot, it's very nice to be able to have a continuously differentiable function that you can just kind of learn your data for first, and then use that conveniently to find your symbolic regression. It's unclear how performant it would be to do the search inside of the actual like causalized, acausal equations. And I think it's yet to be seen whether or not one would work for the other. So I'm curious, what is your intuition of the performance of doing something like that?
Yeah, I think it is indeed yet to be seen. It does have the advantage that you cut out the noise that is created by your misspecification of your neural network. Like your neural network is never going to fit exactly. So if you cut it out, then that's one aspect that you gain. The downside is, of course, that when you put directly the differential equation into symbolic regression, then you have to solve it again and again. So that computationally it might be more expensive. But I'm also not sure if that's really true, because otherwise you have to put in the neural network into the differential equation solver, which is also very very expensive. So that's kind of depending on how much the code is optimized. Yeah.
We'll have to see.
No more questions? Well, I guess I'm going to have to ask to thank myself again then. Sebastian, of course. Okay, the next speaker can prepare. Okay, our next speaker is Daria, and he's going to talk about how components in Modeling Toolkit can help improve your SciML workflows.
Hi, and yeah, welcome to this talk. It's all about designing SciML components in Modeling Toolkit. And I'm fairly sure a lot of people here at JuliaCon have used Modeling Toolkit. We've seen that in previous talks as well. So this talk is designed to be a bit more on the practical side on how do you actually construct surrogate components for scientific machine learning in Modeling Toolkit, and how do you actually incorporate that back into your workflows. So to give a quick walkthrough, we're going to be basically going over a problem setup, fitting to data, some surrogate construction workflows, and finally exposing the surrogate in MTK and then downstream tasks. So a lot of very interesting problems have been brought up over JuliaCon and in various domains as well. So I'm going to bring it back a little bit to a more simpler example so that we can actually walk through what we're actually trying to accomplish. So this is the setup. It's basically a simple pendulum, right? And I may not be the best modeler, so bear with me when I construct my mathematical pendulum. It has the classical equations that you would expect written in Modeling Toolkit. So what is next? We will now construct this pendulum for real, and finally we'll try to match any data that we can get from that real pendulum to the one that we have modeled here. And finally, profit. All right. So let's take some experimental data. So imagine we construct this actual pendulum. We hang it from a pivot. We actually started from some initial conditions, and then we let it go. And we track the progress of its angular velocity and angular position over time. So that's the basic setup, right? So we have some data that we have collected from the real world, and we have a model that we are very confident actually simulates that. So let's first of all simulate our system, right? And let's look at what that looks like. So this is a very simple animation that basically shows, okay, this looks pretty good, right? Like we have a pendulum and it's doing its thing. That's what we expect it to do. So let's try to match it to our actual data set. That's what we're here for. And we see that it's not doing all that well, huh? Well, that's not a big deal because we have some interesting tooling in our hands. We know that we can fit the parameters. This was a mathematical pendulum. And we don't really know exactly how the experimental pendulum was designed. There might be some discrepancies here or there. So maybe if we fit the parameters, we'll get better results, right? So that's what we're going to do. We're going to go for this amazing package called Dyad Model Optimizer. It's part of the Dyad language. And you can see very easily what we're trying to do here is we're coming up with an experiment. We're going to construct an inverse problem, and we're going to calibrate these parameters. That's how you would expect it to do, and that's what we're doing. And let's look at the results, right? We see that it was able to calibrate. We're only calibrating two things. In this hypothetical condition, we're expecting that we can change the length of the string as well as the gravity for weird reasons. But we see that we're actually able to calibrate and we get some results. So maybe this time around, our pendulum will actually fare better. It's a bit better. Seems fine. But it seems to lose track. It seems to lose track of our actual data. So even with the calibration, it doesn't seem to go all that well. So what are we missing here, right? Like we know that we're missing something about the physics of the system, but we may not have the ability to actually find these terms very easily. We saw talks previously in this track as well as during JuliaCon in general, which spoke about finding these missing physics terms. But really what we want to do is actually let the computer discover it. So we want to go for a more of a data-driven system, but one where we can actually train on continuous data, or train rather on discrete data, but actually be able to evolve on continuous time data. But first, for that, we need to collect some data. So let's assume that what we can do is we can take this pendulum, we can start it from a different position, start it with a different velocity, starting velocity, and change the lengths and the gravity and so on, and let's try to collect some data. So this is what that would look like potentially, right? We have a bunch of these pendulums just doing their thing, and we're just gonna collect this data. for us right now. And let's look at what that looks like. So you can see some easy statistics around what this kind of system would look like. But that's the very simple part of it, right? Now we're going to use this data to actually train a surrogate. So we've introduced in the past our digital echo. So this is also part of Dyad, and you can see we're just going to call a basic simple. We're going to take the experimental data and we're going to train a digital echo with it, and this is what that training might look like. And you can see that our training loss has in fact converged over time. So that's all well and good. Now we have the equivalent of a neural network. So don't mind this too much. Our initial parameters for the length were basically too long for it to actually fit in screen. But you can see that it doesn't look all that great. But we still know that we're still supposed to fit our parameters to it. So let's take a step back first. Let's look at the surrogate structure from a modeling toolkit perspective. So what's happening? The first block that you see here is describing the various variables and parameters that are part of our actual modeling toolkit system that we wanted to surrogatize, that we wanted to actually collect data for. And on the bottom, what we have is the structure and the various variables that we would use for our surrogate. Now, you would notice one thing is that all of these components are all arrays, and we want to be very sure that we can actually preserve the array structure, because that is going to be very important for us to be able to performantly actually evaluate our model within modeling toolkit. Because otherwise, if we were to do it symbolically, purely symbolically, it would require breaking our arrays down into very inefficient structures, causing us to actually lose performance, which is not what we want. So as you can see, we define a dedicated P structure, a dedicated union structure, and we actually just, as is tradition in modeling toolkit, anything that you just want in your system, you're just going to shove it into your parameters. So there you go. Our model is now a parameter. All right. So what do the surrogate equations look like? So modeling toolkit, as we've seen in previous talks, and we know very well, modeling toolkit can and will reorder all of our equations, our parameters, our execution orders, in order to actually gain some kind of insight into the model, simplify, do symbolic expression elimination as well. So, but we have to be very careful that we have to preserve our neural network structure, because that is what is a black box modeling toolkit. We can do that fairly simply. What we're going to do is we're going to define our U effectively as the output of the model, and let modeling toolkit not worry too much about it. One thing to note here is that we want our original symbols to be available in our surrogate, and in order to do that, we have to create parameter dependencies which track from our original model back to our surrogate, such that we can still call on those symbols as needed, ditto for our variables, but without letting modeling toolkit actually destructure those structures that we had spoken about earlier, in order to maintain our performance characteristics. And finally, by not providing defaults at the very first level, you can see in the equations we don't provide any defaults. And previously here also, when we define our parameters, we don't actually give it any defaults. The reason for that is we want modeling toolkit to actually solve for these parameters when we actually change them over time. So therefore, we provide the defaults in the dictionary and not in the when we actually allocate our P. All right. So what does that look like when we put it all together? So this is what it would look like. You can see that we have our variables from our original model existing as variables for the surrogate itself, and even the parameters. Well, you can see P1, P2, P3, P4, but what they actually represent are the parameter dependencies that we have demonstrated, that we have generated previously for the purposes of getting those values later on, not right now. All right, so what happens if we try to solve the surrogate, right? We do the very straightforward thing. We have our modeling toolkit model, we construct our ODE problem, and then we solve. Weird, right? It's empty. What happened there? Where did our surrogate go? I mean, it wasn't the whole point that we were supposed to do this fast, and like, I wanted fast, but I didn't want it to just not do it. So turns out the reason for that is something quite interesting, but very simple, can be explained. Our original system had some variables, had some unknowns that we were solving for. However, those systems were mechanistic expressions that we could actually track and actually evolve over time. For a surrogate, especially a data-driven surrogate as we have here, the parameters don't really have any physical meaning. The equations don't really have much physical meaning. All we know is that they have some outputs, and those outputs can only be represented in the form of observables. So from a modeling toolkit perspective, whatever output that we provided from our surrogate was nothing that it needed to actually keep track of. It didn't need to solve for it because it would always get it when it needed to, and there was no dependency elsewhere from any of the other components. So therefore, modeling toolkit decides never to solve for it, which is exactly what we would want, right? Because our surrogate is still in there somewhere. It means that we can call on it whenever we want, however we want, by preserving all of our structure and therefore computational complexity as well, without having to compromise on our actual ability to actually hook it together with different components later on. All right, so let's move on. So we're going to be doing some parameter fitting. We saw earlier what this looked like. It looked kind of weird. Again, because that's the data that we used to train our model. It picked up the first equation, the first set of parameters it could get in order to construct a default pendulum for us, which looked a bit awkward. But now we know that we need to actually fit these parameters from our surrogate to actually make meaningful progress here. So let's try to do the same process for parameter fitting on a surrogate. So as you would have remembered from previously, we use dyad model optimizer again, and this is again what this would look like, right? You would imagine, you could see that the actual, I don't know if this is visible. Yep. So you can see that the actual parameters that we're actually allowing model optimizer to actually tune for are remarkably similar to the ones that we had for our original system. Whereas this time, we're going to be changing it for a surrogate itself. And again, let's try to calibrate, and boom, we have some parameters. Let's hook this up back into our system and see what it does. Much better, right? So one thing that I haven't mentioned, and the keen-eyed amongst you might have noticed, is if I were to go back quickly, right. So the calibration originally took us 14 seconds and 14 and a half, and gave us about 1u minus 1 about loss for the error objective. All right. But our data-driven model, on the other hand, was able to finish in under a second and give an order of magnitude lower loss on our objective. So by being 15 times faster, as well as an order of magnitude more accurate compared to our original flawed system. So this example was chosen specifically to demonstrate, well, what was that missing physics, right? So there was clearly something missing from our original model. And let's just look at the comparative results between the two, right? So our original system clearly had something missing in here, whereas the surrogate was able to take the data and actually fit to the data in a manner which could also interpolate within the given parameter regime. All right, so this was just the model discovery process. I mean, I'm calling it model discovery, but I'm using the term kind of lightly because even though this is a fully fledged surrogate, it is also highly data-driven, which is kind of what we want, right? We want a mix of, first principles modeling, as well as fitting to experimental data to get an overall model which is actually more accurate and faster to solve overall. So our surrogate learning process contained 100 parameter samples, and the term that it was actually missing in our original system was effectively the damping, which is again something that you would learn in an intro to mech course, but in our simple model, we chose to eliminate that term in order to be able to demonstrate that we can actually use a surrogate to fit into physical expressions that may not otherwise be very obvious. Now, this is just a demonstration. Of course, when you use it in more complicated cases, you will be able to solve for more different residual terms as the problem sets may arise. And we have had some excellent talks in the past talking about those kinds of problems as well. So one thing important to note is that this method itself does not actually recover any of the symbolic expressions as you would expect with the UDE, because this is not a UDE, this is just a surrogate. But it does actually behave in a physical manner with the physical constraints that we have actually trained it with. Now, in this case, again, this is data driven, but you can imagine collecting data on a more constrained system in order to get the same kind of behavior. Okay, so this is something that I wanted to talk about. We spoke about how to actually make these calibration results going, right? And I wanted to side-by-side comparison of what this would look like for our original model versus our surrogate. Just to give you an idea of whether or not we were able to faithfully recover the kind of structure that we have for our original system, and still be able to use it, but just in this case, it's a surrogate. But it's still completely, transparent to the user in terms of what actually is going on. So you can see we're using the same symbols, we're using the same exact API without having to change any excessive, code there. So that's important. The only major change was rather than having just a simple model.pendulum, here we have the surrogate pendulum.component. We'll come to why that is in a bit. So again, with modeling toolkit, the other thing that we would expect to do is if we have a component, we would want to actually connect it to different other components. And in this case, we're just going to use a simple controller. This is a very simple Gaussian force controller, nothing too crazy. But you can see, again, the idea of this demonstration is to basically show how remarkably close the same surrogate model looks like from the original model, such that you don't, as we speak about in JuliaLang all the time, right? Like you write your code once and then you can deploy it in multiple different ways. It's very similar here. You write your code once, but you're able to then train a surrogate and then just replace your component that you surrogatized with the surrogate without having to do any extra work on it, and still get the benefits of any kinds of problems that you were facing with the original model, be that with performance, be that with speed, be that with physical constraints. All right. So the next topic that I had is FMUs. And FMUs are these things called the functional mockup units. Effectively, this is a standard format that a lot of simulation software has come up with in order to be able to ingest components into their various software libraries and be able to connect them in one place. So can we export these MTK components, and not just MTK components, we're talking about a surrogate here, into an FMU as well? And of course we can do that. We have this package called FMU generation, also part of Dyad. You can see the API for that again looks remarkably similar to what you would for a regular component. And after this, I have a quick switcheroo. So you can see on this tab, I have FMPy loaded, and I have loaded in my original model with the controller attached to it. You can see that here. You can see that it simulates as we would expect, and ditto for our surrogate. In this case, this is not going to connect to a controller because it wasn't trained with the controller in the first place. But in general, as we can, you can see that it has the same kind of oscillating behavior that we would expect from our original surrogate as well. So we were able to convert it into an FMU, load it into FMPy, connect it to different other components, simulate. Excellent. So I'm doing just a quick look back. So again, our original model did not fit data because it was missing certain terms and components that we were not aware of at the time. Ultimately, trying to fit it into actual experimental data gave high prediction error. and the low fidelity model couldn't fundamentally fit any of the physics that we were actually interested in. Our data-driven model, however, was able to actually identify the hidden components, again, while actually discarding any of the equations that we were actually interested in, trained still with continuous data as before, but combining the physical information from the data that we gathered plus the surrogate itself, training it in a data-driven manner, allowed us to actually have a more accurate surrogate overall. Yep. And of course, we can use this technique beyond pendulums. This 500 plus shouldn't be there, but in general, there's a lot of different interesting problem sets where problems like this can and have been shown to been of use. And the key takeaways are that you start with the physics that you know. You let your data reveal what you can't know ahead of time, and you combine them for better results to come up with a hybrid model. We've seen in various SIML talks as well how the future of modeling is going in that direction, where we are trying to leverage both the physical information, the physical mechanistic equations that we can actually control versus the experimental data that we collect, which will still have some kind of error from our even a high fidelity model. There are other approaches, of course. Sebastian here gave an excellent talk about UDEs as well as James. So these were other talks that I would have recommended as well to actually come up with a different approach to this, where you actually don't want to lose track of the equations and try to use the neural network simply to augment it and to find those symbolic expressions that are required to do your error correction. So these are just some of the talks, but these are just the previous talks from the same track because of scheduling. But yeah, it's still brilliant work over there. So yeah, big shout out. But yeah, thank you. And if you guys have any questions, I'll be happy to take them.
Questions?
This is sort of a basic question. I didn't fully track the what's going on inside the surrogate. Is that just like a neural network that's learning the right-hand side of differential equation?
You can think of it as a neural network for sure, because what the surrogate is a little bit arbitrary in this case. In this case, it was a digital echo. This is something that we have demonstrated earlier as well, designed specifically for dynamical systems. Having said that, the idea here was to show basically that you can actually take data that was taken from dynamical systems, started with various initial conditions, parameters, so on and so forth. So we take our discretized data, and we still are able to then work with the continuous symbolic evaluation, integration that we would otherwise do with a dynamical system. So that was the kind of demonstration that we were going for.
More questions for the speaker? If not, then I think we can conclude this session. Let's thank all the speakers once again.